What's better and like Lisa. Lisa, how can you solve this question? Right, I've read it up, but I can't really understand.
So over the time, I've received a lot of complaints, a lot of suggestions from the students. Tell me that a particular topic was given a lot of problem, tough time in understanding it. That they've gone through several textbooks and still not been able to understand what the topic is all about. Even when they try using solving questions after the topic, they find it difficult to understand it. I'm very sure others also have the same problem. That's why, in partnership with Gallant Tutors, we've come out with an initiative to make this teaching available to everyone. I mean everyone. As long as you're a student, this video will be beneficial to you. So what's this topic all about? What's the name of this topic? I'm very sure that I'm giving you suspense already, but don't worry, I'll reveal it soon. So this topic, after my discovery, after my research, I found out that is the easiest. When I mean the easiest topic ever, because it's something we can relate to. It's something that makes up our body. It's something that we can find all around us. What's the name of this topic? The name of this topic is organic chemistry. So during the course of this video, we'll be treating about organic chemistry. We'll be talking about organic chemistry, and along the line, I'll also be discussing some certain terms, some certain subtopics that are necessary to you, that are necessary for you to understand what the topic is all about. Alright, so what are we going to be discussing about? So we'll just be discussing chemistry and also organic chemistry, which is the main reason why this video was made. We'll talk about that also. And also hybridization. We'll define what hybridization is, take some questions on the hybridization. Right? After that, we move to functional groups. A lot of people mistake or don't even understand what functional group. Sometimes they feel that functional group and homologous series can be used interchangeably, which is wrong. So during the course of this video, we'll distinguish the fact between functional groups and homologous series and make it very easy for you to remember. Also, types of organic reactions, we'll be talking about it in this video. Factors affecting organic reactions. As you know, even as we are living right now, we are living in your home, there are some factors that make it possible, right? If that place was a swamp, you might probably not live there. The same thing occurs in organic. The same thing occurs in chemistry. So we'll be talking about that too. And our main focus for today will be alkanes. Alkane. I would have loved to cover everything about organic chemistry just in one video, but that's not feasible. I don't want it to be so long, right? I want you to enjoy your stay here. So if you're new, welcome on board. Welcome. Thank you so much for being here. Thank you so much for clicking on this video. I believe that you have a good time here. Alright, we'll go on a short break, and when we come back, we start. Alright, welcome back guys to Gallant Tutors Academy. So just like I said, we'll be taking it in steps. So this video will be divided into several sections based on what I said in the prologue. Alright, first things first, what exactly is chemistry? When we say chemistry, what do we understand by it? Alright, it's not a big deal, it's very easy to understand it. So when we talk about chemistry, we are actually discussing about the scientific study of matter, right? So we are talking about its properties, its compositions, structures, and changes it undergoes during chemical reaction. So whenever we discuss about this, we are actually discussing the chemistry of matter. Do you understand? So we talk about the changes it undergoes during chemical reaction. Also, chemistry also explores the fundamental principles that governs the behavior of atoms and molecules, enabling us to understand and manipulate substances that make up our world. You can see that chemistry is actually very, very important. Now, organic chemistry is simply a branch of chemistry. Organic chemistry is simply a branch of chemistry. So when we are dividing, we can say organic chemistry, right, is simply a branch of chemistry. So what's the other branch like? What's the other branch like? The other branch is actually the inorganic part, the inorganic chemistry, right? So now I'm not really talking much, I will not be discussing much about this inorganic chemistry, but I will be discussing more about organic chemistry, right? So now, what do we understand by organic chemistry? When I say organic chemistry, what does this mean? Organic chemistry is simply a branch of chemistry, as you know now, that specifically focuses on the study of carbon compounds. So when we are talking about organic chemistry, our main focus is actually on carbon compounds, right, which are essential for life on Earth. So carbon atoms have a unique ability to form stable bonds with other elements, including carbon itself, giving rise to an enormous diversity of organic molecules. Organic chemistry is concerned with the structure, the properties, the composition, reaction, and synthesis of all these carbon-based compounds. Also, organic chemistry plays a vital role in various scientific fields such as medicine, biochemistry, pharmacology, material science, and many more. It allows scientists to understand and design drugs, study the structure and function of biological molecules, develop new materials with specific properties, and explore intricacies of chemical reactions involved in organic processes. So you can see that organic chemistry is very broad, as it consists almost every part of us. Like, it's very, very common around us. Therefore, a session of chemistry has actually been dedicated for it. Now, let's dive in. Oh yeah, so let's move on. We're going to the next session now. All right, every topic, every course has something unique that it has something unique, right? Organic chemistry inclusive. So there's actually a particular concept, or will I say terminology, that you have to be familiar with, you have to understand. Do you understand? So what's it? What's this term? It's actually what? Hybridization, right? Hybridization. So in your study of organic chemistry, you will encounter this most of the time. So now, this hybridization, so what does this actually mean? In simplicity, it actually means mixing. So whenever you hear hybridization, it actually means what? Mixing. Alright, expatiating on this, hybridization is actually attributed to orbitals. So whenever we talk about hybridization, we're actually what? Connecting it. We're actually directing it to what? Orbitals. So this actually involves mixing of atomic orbitals to form new identical orbitals known as hybrid orbitals. So it's simple. We have different orbitals. Orbital 1, let me just call this orbital 1, then plus orbital 2, and when we mix it together, we should normally we also get probably like orbital 1 2. Doesn't happen that way. We just call it what? 3 orbital. They merge together to form what? 3 orbital. So this is exactly what is actually happening in hybridization, right? So now let me, probably for those who are new to chemistry or those who don't really understand what orbital is, I will explain it. First of all, you have to understand that there is what is known as shells, right? So how is this shells like? Shells are actually represented by letter K, L, M, right, N, O, etc. And how is this like? How can we describe this shell? It's actually talking about where the electron reside. So according to Rutherford model, we have something like this, right, which is the nucleus, and surrounding the nucleus are circular orbits, right? Circular orbits where the electron actually resides in. Do you get that? So this particular stuff you see here, this stuff are actually the shell. Like for instance, this one is the K shell, this particular one is the L shell, and this is what? The M shell, and on and on and on and on like that. Okay, so let me try to zoom this shell, though it's not possible. But in this shell, right, in this shell, we have what is known as the subshell. We have what is known as the subshell. So when we talk about the subshell, what are the subshell? The subshell actually includes a minute. Are represented by SPDF, right? So the subshell are found in this shell are found here, right? So even in this subshell, we now have what is known as orbitals. So in each subshell there are orbitals. For instance, the S has only 1 orbital, the P has 3 orbitals, the D has 5 orbitals, right? They have 5 orbitals. This, like this, it actually occurs this way, 5 orbitals, and this has what? 7 orbitals. 7 orbitals. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. All right, 7 orbitals. So that's why when you were taught this electronic configuration, you do write it this way: 1s2, 2s2, 2p6, on and on and on like that, right? It actually signifies the number of electrons in each subshell, right? The number of electrons in each subshell. For instance, the S has only 1 orbital, and each orbital can only accommodate 2 electrons, right? So these 2 electrons here, right, for S, that's why we have to write what? 2 here. Do you get? So for the P, it has 3 orbitals, so 2, 4, 6, and it actually what coincides with what is written there, 6 orbital. All right, what of the D? The same thing. F, the same thing. So this hybridization, if for instance, let's take carbon, since we're talking about carbon mainly, let's take carbon. Carbon, what's the atomic number of carbon? 6, isn't it? 6. So we can write it this way, according to shell configuration, 2, 4. Right? We can write it this way. Or we can say 1s2, 2p6, 1s2, sorry, I made a little mistake there. 1s2, 2s2, 2p2. So 2, 4, 6, which actually what coincides with it, which actually what the same as this 6. So in this part we have just 2 electrons here, and for here we have 2 electrons too. So how does it accommodate? Just 1 and 2. Here 1 and 2, right? But it can actually form bonds this way. It can actually form bonds this way. This one will have to be excited into this particular orbital, right? That's be excited into this particular orbital. So we end up having something like this for the 2s, for the 2p. We end up having something like this. You understand? We end up having something similar to this. These are orbital in the excited state. So carbon is capable of forming 4 bonds through hybridization. Through this, it's capable of forming 4 bonds through hybridization. Alright, so what hybridization does is that it merges these 2 orbitals together to make it look like one, and not only make it look like one, to have the same energy. Because as it stands now, this particular 2s orbital you are seeing now, right, it's actually on has a different energy compared to this. This orbital, they all have the same energy, definitely, and they are known as degenerate. But it's actually the energy it has is actually different from this particular one. I hope you get it now. Good. So what it does is that this S, how many P are here? 1, 2, 3. sp3, right? So what's its form? Like when carbon undergoes hybridization under normal conditions, it forms 4 sp3 orbitals. Do you get that? It forms 4 sp3 orbitals. Alright, so just like I was saying, that carbon, just for recap, carbon has 6 electrons, right? And also it forms, after it undergoes hybridization, it forms what? 4 sp3. But you should note, this is not always the case. So this brings me in to tell you that there are 3 types of hybridization, right? There are 3 types of hybridization. And what are they? It's actually very easy to know them. The first one is what I've discussed, which is sp3. The second one is sp2, and the last one is what? sp. The way they form are actually very, very similar. You get? They're actually very, very similar. And first of all, for you to understand each and every one of them I will be explaining, you have to understand the electron configuration of carbon, right? So carbon is 6. If it's 6, it will be written as 1s2, right? 2s2, right? And then 2p6, something like that. In orbital configuration, we can say, we can do something like this, and it still counts, just like what I said. So we have 1, 2, 1, 2, 1. So here will be 2. Please take note. 2, 4, 6. So 1, 2. So from here now, it must always, this one electron here must always be promoted to this. You understand? Because there is a higher tendency of carbon forming 4 bonds. Okay, so it can never form 2 bonds. So there will always be promotion of electron from 2s, right? There will always be promotion of electron from 2s to what? To 2p orbitals. So it always happens. It's not actually something that happens one time and doesn't happen another time, right? Okay, so let's promote it. So it becomes something like this. Alright, so this is what really happens. So you can see it has like four possible, it can form 4 possible bonds based on this illustration given here. Alright, so what really happened was that in the sp3 is that all of them blend together, mix together, which is hybridization, right, to form 4sp3. Do you get that? And it's peculiar, it's actually peculiar to a particular organic compound, right, or functional group, which is known as alkane. The alkane are very, very special and undergo this part of hybridization. So this is what really happens when they form bonds like this. It's not actually written this way, you know. S is spherical, isn't it? So I can say it's spherical, and then our P is what? Dumbbell shape, I guess it. So we will having something like this. Do you get? Something like this. You can either I drew mine vertical, you can draw your own horizontal. So when they, after hybridization or after mixing, they actually form something like this. I get it. So they form 4 of this. This is sp3. They form 4 of this. You get? So this particular stuff you're seeing here has the characteristics, this particular shape, right, has the characteristics of both S and P. It has the characteristics of both S and P. And whenever it forms this way, it actually rearranges itself, you get, into a tetrahedral geometry, right? Into a tetrahedral geometry, it comes to look this way. So something like this. It forms something like this, right? It forms something like this, and each bond here, there is actually a bond here, there's a bond here, there's a bond here, right? So each bond is actually a sigma bond. I feel it. It's actually a sigma bond, but this look vague. Let's explain everything using alkane, and I'll use its first member, which is methane. Methane is written as the chemical formula CH4, right? Methane has the chemical formula CH4. Alright, so we have C, which is our carbon, right? We have H, we have H, we have H, we have H. Remember that this C, based on what I explained here, right, has 4 sp3 hybrid orbitals. Do you get? So one of the sp3 forms bond with this, one of them form bond with this one of them form bond to this, one of them form bond to this. Do you get? Forming something like this. So it forms 4 sigma bond. It forms 4 sigma bond. This is a 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 sigma bond. So this shape you are looking at like this is actually similar to this, right? It's actually similar to this, and it's known as what? Tetrahedral. So the shape of any molecule, right, organic molecule to be precise now, that has sp3 hybridization is actually what? Tetrahedral. Now remember, this is not like the way I drew it now. It looks plain, it looks as if this height actually occurs, but it's actually a 3D structure, right? It's not a planar structure, it's actually a 3D structure. So the angle between these parts, the angle between here is what? 109.5 degree. You should take note of it. It's usually asked in O-level exam. So the angle between this and this is 109 degree, 109.5 degree. The same thing goes here, here, right? So the same thing goes there. But you might be thinking that why is it not 90? Since there is tetrahedral, as I said before, it's not a planar structure, it's actually a 3D structure. So please take note of that. So apart from this carbon here forming bonds with hydrogen, right? Remember, hydrogen is S. So form bonds with hydrogen. It can also form bonds with chlorine, such as chloromethane, right? Chloromethane, which is what? CH3Cl, something like this. So if it forms like this too, it's also similar. Remember, this is in the p. This is like, this has a p orbital, right? Instead of an s, according to H, it has a p orbital. Do you get that? So so this sp3 in this bond here bonds with p, but in this bond here sp3 bonds with what? S. Hope you know. sp3 can also bond with sp3. sp3 can also bond with what? sp3. How can we see this? We can see it in ethane, right, which is C2H6, isn't it? Okay, let's see how it goes. So we have C, something like this, right? And then we have 1 2 3, 1 2 3, which is 6. Just fill in your hydrogen. Okay, so this and this you should know by now is this sp3 and s, sp3 and s, sp3 and s. But between this one and this, what kind of bond is there? It's actually what? sp3 and what? sp3. So this sp3 can actually bond with sp3. It can also bond with s. It can bond with what? sp. It can also bond with p, I mean to say, right? So she take note of that. All right, so just a quick recap. Let's just a quick recap or summary of what sp3 is all about. So we should know that sp3 has a tetrahedral shape, right? Remember, it's not planar. Please do not forget, it's not planar. Planar means that it's kind of, it can be represented on a flat surface. It's not 3D, so it's not planar, please. So the bound angle is 109.5 degree, right? And it's responsible for the formation of alkane, which is saturated hydrocarbons, right? So let's talk about the sp2 now. Let's discuss about what you mean. Let's talk about it. So on to the next type of hybridization, which is sp2 hybridization, and it's also exhibited by carbon. Please take note. The one I explained before is also represented by carbon, which is sp3. So this involves the mixing of one 2s orbital and 2p orbital, right? That is, what is formed here is actually 3 sp2 hybrid orbitals. So how does this look like? First of all, let's represent carbon, right? Like its orbital configuration. Okay, so this is how it looks like. It's 6. We have this, right? Okay, so we have alright, just it looks like this, right? So this is how it's represented. So definitely this would migrate to this place, right? It's migrate there and it will form something like, let me just show you here. I just don't want to waste time, right? It forms something like this. So 4 orbitals with single electron. So in this sp2 hybridization, it's only one of this, right, and 2 of this that actually mix together to form a hybrid orbital. Unlike the sp3, whereby this one, this and this mix together to form sp3, it doesn't happen like that in sp2. Alright, so when it's mixed together, it forms 3 sp2 and what? Unhybridized p orbital. Unhybridized p orbital. Alright, please take note of this, that all sp2 hybrid orbital lie on the same plane. All sp2 hybrid orbital lie on the same plane, right? What do I mean by that? So since it's 3 sp2, right, it's going to look something like this. It actually lies on the same plane, unlike the sp3, which does not lie on the same plane. So this part we can use since it's planar, we can actually use mathematics to solve it. So 360 divided by 3, which will give us what? 120 degrees. So the angle between this and this is actually what? 120 degrees. Here, you understand? Alright, so the angle between this and this is what? 120 degrees, and it's also what? Planar. So what kind of shape is this? If something is like this, what do you say? Look at this shape is what? A trigonal shape, right? This is what? A trigonal shape. Trigonal shape. Alright, so now let me give you the implication of this unhybridized p orbital that is here. What does it implicate on the structure? Now this is very peculiar to a particular compound known as alkane. Please take note of this E, unlike the other one that is A, right? So it's peculiar to this alkane. Okay, so what's the first member of alkane? Alkane is actually what? 18. It's actually 18, which is what? C2H4. C2H4. So it looks something like this. It looks like this. So if I write something like this, am I correct? Definitely I'm not. There's something missing, because as I told you, it has 4 ways in which it can occupy, like 4 places for occupying electron. So carbon must always form 4 bonds. It's a must. It must always form 4 bonds. And this 1, this 2, this 3. So remaining 1, how would that one come from? Because we've exhausted our hydrogen. We've exhausted the hydrogen we were given. So that's when we will now know the importance of this unhybridized p orbital. It comes here and forms here. I get it. It forms the double bond, right? But this bond is given a very special name known as pi bond, right? It's a type of covalent. Remember I told you that this is a sigma bond. This is a sigma bond and this is a pi bond. Let me just brief you a bit about the sigma and pi bond. This sigma bond you see here is actually very, very strong bond. It's very strong. It's stronger than the pi bond. You get? And it's the first type of bond that is formed. It's stronger than the pi bond and it's the first form of bond that is formed. This pi bond is not that strong. It's strong though, but not that strong. But the main characteristics of this pi bond is that it makes the compound more reactive. It makes the compound more reactive. In this case, alkane. It makes alkane more reactive. Do you understand? So if I'm actually comparing alkane, which is the one that ends with ANE and ENE, right? If I should ask you, which one will be more reactive? It will be what? Alkane. Alkane, that is this particular one will be what? More reactive. Why? Because of the pi bond. This does not have a pi bond. It only has a sigma bond only. It has sigma bond only. And just to reiterate, the pi bond is formed by the overlapping of the what? Pi unhybridized p orbitals. Unhybridized p orbitals. Please do not forget. Do not forget. So for the summary, alright, for the summary, so key takeaway, you should note that for sp2 hybridization, right? It has a trigonal shape. Also, the bond angle is what? 120 degrees. I said so. And it's peculiar to alkane, to compounds alkane. Remember E. A is for the one. If I replace this E with A, is what? The sp3. Please do not forget it. Alright, so that's all for that. So let's move on. Let's move on to the sp2 now. The sp alone, sorry, the sp. So it's obvious. It's formed from the hybridization or from the mixing of 2s and one of the 2p orbitals. You get that? One of the 2p orbitals. Just for recap, let me just draw it. I need this thing to stick. You have to understand it. So this one is So this particular stuff is actually formed from this guy and one of this guy. You get? So we are left with 2 unhybridized p orbitals. You should have guessed the number of pi electrons we should have. Oh, no problem. Just follow me. Now, it forms just 2sp. 2sp. You get that? So what this is trying to say is that I'm capable of forming only 2 sigma bond. That's what this particular stuff is talking about. Are you following? Alright. So where can we see such a compound? It's peculiar to what? Compound alkene, right? Alkene. So from this, the first member of homologous series alkyne is actually ethyne, right? Ethyne, which is C2H2. You understand? C2H2. Remember, it forms only 2 sigma bond, which corresponds to this. Right. So let's draw it. C1, 2, H here, H here. So, but this is not complete. It still requires 2 more bonds for this carbon to be stable. It requires 2 more bonds to be stable. So how do we get those bonds? Right? It's actually from what? The unhybridized p electrons. So they'll come here, form 1, 2. Right? These particular stuff are the pi electron. Are the pi electron. Are you following? Are the pi electron. So this functional group ethyne has more pi electron, right? Therefore, it's even more reactive when compared to ethene and alkene, right? So during the course of this video, as I explain more about it, you'll be able to understand the difference, the kind of reaction that alkyne passes, the kind of reaction peculiar to each of these functional groups I talk about. Lastly, let's talk about the electronegativity of hybridized orbitals. That's also a key point to take note of. Alright, so the electronegativity of hybridized orbitals. So it's actually not a big deal. It's not a big deal. You just need to take note of some certain terms I'll be saying, right? So we'll be comparing sp, right? sp2, right, and sp3. You get? Remember, I didn't remember to tell you guys what's the bond angle of sp. Since sp is linear, what would the bond angle be? You can guess that 180 exactly. So this is what 180. What is this? What's the bond angle? 120 degrees. What is 109.5 degrees? Please do not forget, it's very important. So now, as I told you, it's not a big deal. The electronegativity of the hybridized orbitals is not a big deal. The greater the s character, right? The greater the x character of a hybridized orbital or a hybrid orbital, right? The greater the electronegativity. So let's get this into words. Let's get this into words. The greater the s character, the greater its electronegativity. Right? So let's know between this and this, which one do you think have the highest s character? Okay, this one has 1:1, right? This has what? 1:2. I'm considering this. There's an invisible one here, so this has what? 1:3, isn't it? So which one do you think has the highest s character? It's obvious. This has the highest s character. So according to what I said the greater the s character of a hybrid orbital, the greater the electronegativity of the orbital. So this has a higher electronegativity value compared to this. So therefore, this also have a higher electronegativity value compared to this. Please do not forget it. Also, the increasing p character, right, of the bond decreases the increasing p character of the hybrid orbital decreases the bond angle. You can notice that this is increasing, p is increasing from 1, 2, 3. So as p increases, the bond angle does what? Reduces. The bond angle what? Reduces. All right, let's move on. Let's go to the next part of our lecture. All right, over to the next section, which is what? Functional group. Now, this is also something you must take note of, right? It's something that as we go along, we continue this video, you'll be able to know more about it, right? It's a very, very important term. So when we talk about functional group, what do we mean by that? Functional group. So this is, let's first of all break it down before I define it. So from here we are discussing what function is. So function and a particular group. So I think based on this, we are actually talking about a particular group that serves a particular function, right? A particular group that has a very, very unique function. Do you get? So that's what this heading is really talking about. Okay, now let's move on. Let's move on. When they talk about functional group, this is what they simply mean. It's whenever we scientists or chemists say functional group, they're actually discussing about atoms or groups of atoms responsible for chemical identity. So therefore, this functional group you see are actually what? Responsible for the chemical identity. The chemical identity, right? The chemical identity of a compound, or you can say of an organic compound, or now of a compound. Do you get? It's simply a term used to identify organic compounds and differentiate them between two or more organic compounds. Is that clear? So the different functional group constitutes of different homologous series. The homologous series, most students confuse the functional group from what? Homologous series. But they are similar, but they are very, very different. Do you get that? They are also very, very different. Homologous series. Okay, see, let me explain to you. I'll first of all talk about an example of a functional group. Right? I'll discuss what the functional group, like some example, then I'll explain to you what homologous series is all about. Let's take alkanol for instance. So alkanol, we all know that this is an organic compound, isn't it? The first member under this group is what? Who can guess that? Ethanol, correct. Ethanol, right? Let's also consider alkanoic acid alongside. So what's the first member of alkanoic acid? Is what? Ethanoic acid. Ethanoic acid, exactly. So let's draw the structure. Let's draw a structure of this, or probably its chemical formula. So this is what? C2H5OH. What is this? This CH3COOH. Do you get that? So probably when you draw a structure, you'll be able to understand it better. So let me draw a structure. So it looks like this. It simply looks like this. Right? This, and this. Let me use another color of pen for this. Okay. So we have OH here. Right? We have OH. So for the other one is similar also. Similar, we have C. Remember this and this. So we have CC, right? 1, 2, 3. This is for the hydrogen. I didn't notify for the other one. This is for the hydrogen. So this forms double bonds with one of the oxygen and one single bond with OH group. Do you get that? Oh, so let me use another pen for that. Alright, so this forms like something like this. This is what it forms. So what differentiates this and this? It's actually what? This particular part. Right? And for this is actually what? The OH group. The OH group. Okay, let's move on. The OH group. Alright, let's move on. You see this part I circled, right? This part I circled, this particular stuff and this are actually the functional group. Do you get that? Are actually the functional group. That is, they are the one that determines the kind of chemical reaction a particular organic compound will undergo. Do you get that? Look at this. This particular stuff has 2 carbon, right? This one also have 2 carbon. So they are very, very similar, but it's only the functional group that can distinguish them. I usually use this analogy, the surname of a person. You guys attended secondary school or even primary school, right? So not everyone has the same surname. It's very, very rare to find 2 persons that have the same surname. So that you might have the same name, someone might be bearing gift, you also might be bearing gift, but the surname is kind of so unique, so distinct, right? So distinct. So the surname actually, when they call, oh, probably your surname is Okoro, you say Okoro, without even thinking twice, you will know that, oh, this person you're talking about, right? But when we talk about gifts, where is gift? You're like, sir, are you referring to me? Right? Because there are a lot of gifts. You get. So when someone asks you what's the characteristics of a compound with 2 carbon atoms, you can't give a definite answer. Do you get that? Because look at this now. This have 2. This have 2. So you can't really say, oh, it has so this. It has so feature. No, except you are being told the functional group. So this functional group is very, very distinct, right? Very, very distinct. All right. So under this alkanol, right? Under the alkanol, we have other groups. Under the alkanol, we have other groups, right? So alkanol, we have ethanol, just like what I mentioned there. Ethanol, right? After that, what? Propanol, butanol. Let me just stop here. Okay, so for this, how do we represent it? We say C2H5OH, right? What is this? C3. You know you can calculate it. This is how to calculate it here. Let me just tell you the formula in case you want to solve it there. 2N plus 1 OH. So for this, it will be 3, right? Since prop is 3. So it will be 3 times 2, 6 plus 1, 7. So H7OH. All of this butanol, it will be C4, H what? 4 times 2, 8 plus 1, 9, H9OH. Can you see it? So if you notice, the difference between this and this is actually very small thing. This have 2, this have 3. So let's write it C. This have 5, this one have 7. So what? 2. They have the same. What of this one? 3, 4, still 1. 9, 7, still 2. So they have similar, they differ by what? CH2. Now let me now explain to you what homologous series is all about, since I've established the concept. Now when we talk about homologous series, we're actually describing the series of compounds having the same general formula, right? Series of compounds that have the same general formula, or we can just say the same functional group, and then whereby each successive member, that is the ethanol, the propanol, the butanol, differ, right, by CH2. Differ by CH2. Is this clear? Is this clear? So we know that members of homologous series have similar method of preparation. Do you get that? That's why in your textbook they don't tell you, oh, to prepare ethanol use this method, to prepare propanol use this method, to prepare butanol use this method. No, they will just give you a particular reference, right? They might use ethanol for an example, but you can be rest assured that if you wish to produce other members of that functional group, definitely it will work with a particular method. Do you understand that? With a particular method. So it's worthy of note that the simplest homologous series, or let us say the functional group, is the alkane. The alkane are the simplest, right? The alkane are the simplest. This video will cover alkane, but yeah, this video should be able to cover alkane. So the alkane are the simplest. You should know that. And what's the general formula? CnH2n, right, plus 1H, or I like writing in this way, CnH2n plus 2. So as we go along the course, you will notice that it's actually this that is changing. This changed to OH. Do you get that? But for so please take note of that. Let's move to the next session. Probably I will give you some examples. We'll talk about some classes of this functional group. Then after that, we'll move to the next session. Let me clear this space. Alright, so welcome back. I would like to discuss about some homologous series, like some homologous series that are very, very important. I will not discuss all though. I will discuss some that are very, very important. Then I will try to see the unique features, the unique functional group that it has. So its first member, right? Okay, so for this we can have we can have alkane, which I've discussed, right? So what's the first member? Methane. And what's the formula? What's the general formula? Or let's not talk about only the functional group. It's better, right? So for this, which is methane, it's represented as CH4. So there is nothing unique. It just simply has 4 sigma bond, and they are tetrahedral. They are tetrahedral. So the next one, which is alkane, the first member is 18, right? The first member is 18. It can't be methane because it must form at least 2 bonds with something. You know, hydrogen can't form 2 bonds. It can only form 2 bonds with carbon, which is itself. You get? So that's why we don't have methane. We only have ethane, right? So it's represented this way, CH2, right? The structure is drawn like this. By now, by now you should be familiar with this stuff. Okay, so the next one, which is alkyl, right? Now we have something like this. So how can we represent this? The formula is 2C2H2, right? Which is C123 C11H. I get it. So the next one, let's talk about the alkyl and the alkanol. After that, we discuss about the alkanal. After that, we discuss about alkanone. Okay, I think we should discuss about this, so it shouldn't be too much for you guys to comprehend. So the first member of this, is ethanol. The first member of this is what? Ethanol. Please do not forget it. Ethanol. Right? So the first member of this is methanol. Methanol. The first member of this, sorry, is methanol. I'm used to ethanol already. So methanol, right? Methanol, because it's capable of forming CH3OH. Do you get? You know, I told you now. I'll still come to the formula though. I'll explain to you how this is possible. So methanol. Why for this is what? Methanol. Methanol. And for alkanol, it cannot form methanol. It cannot form methanol. It cannot form methanol. It cannot form ethanol. It can only form propanol, and I'll tell you why. I'll tell you the reason why it can only form so. It can only form that. So the first member of alkanol, of homologous series alkanol, is actually what? Propanol. Okay, now let's look at the formula. Yes, sorry, let me do under pen. Okay, so for this we have C2 CN H2N plus 2. For this is what? CN H2N. Right? I think this is making sense. 2 times 2, 4. So this is CN H2N minus 2. This is minus, this plus. Right? So for this it's simple to CN H2N plus 1 OH. Now let's check it. So if it's 1, if we put 1 here, right? If we put 1 here, it will become C1, right? 1 times 1 times 2 is what? 1 times 2 is 2 plus 1. You get? So 2 plus 1 will give you what? 3. I hope it's making sense now, right? Okay, so you just add your OH to signify its functional group. Why for this? Why for this is actually what? Very similar to the formation of this, similar, but I would like to represent this. I would like to explain it using structure. You get? Using structure. But the functional group of this is CHO. Why for this, right, is just like R. Let me just write it here. R CO R prime. You get? So this is just like RCOH. So this is RCO R prime. Now let me explain both of them so you'll be able to understand it. So for alkanol, we have, if this the R there, the R there represents an alkyl group. An alkyl group. ALKYL. An alkyl group. Right? So it can be methyl, ethyl, whatsoever, right? But I'll be making use of the simplest one, which is what? Methyl, which is CH3. So we can have CH3, isn't it? Then something of dash 0H, something like this. So this particular part, right, is the functional group of alkanol. You get? Of alkanol. What of this one? How is it formed? Now, the reason why such a thing can happen for alkanol is that it must be between two alkyl group. That's the criteria for alkanol. It must be between, sorry, a minute. Yeah, it must be between two alkyl groups. So it must have something like R, then C, this. It must have something like this, something structure similar to this. So this particular stuff here, right, is actually the functional group. You get? It's the functional group. Both of them are both carbonyl compound. I hope you know. So this one, in the simplest form, will be. So this particular stuff in the simplest form will be CH3, right? CO, right? CH3. In the simplest form, it will be like this. Let's see how the structure will look like. Is it balanced? 1 2 3 4, correct? 1 2 3 4, correct? 1 2 3 4. So this is how the structure of alkanol will be like. So that's all for the functional group. Let's dive in more. Let's talk about some of the type of organic reactions, because we'll be discussing about organic reactions, some terminologies, addition reaction, all this stuff. You have to take note of it, because organic chemistry, as I said, is very, very simple. Once you're able to understand all the small aspects, all the things, all the concepts you neglect, then you'll be fine. You should really be fine, right? Alright guys, welcome back. So we'll be talking about, in this session, we'll be talking about the types of organic reactions. Types of organic reactions. So types of organic reaction. Basically, there are 5 types of organic reaction, right? There are 5 types of organic reactions, and they include addition reaction, substitution reaction, elimination reaction, condensation reaction, and rearrangement reaction. Right, so let's dive in. I'll start with the substitution reaction, because it's easier for you to grab that first. Right, so I'll start with substitution reaction. Alright, so for the substitution reaction, what can we say about it? Substitution, just like football, they substitute one to another. They substitute one for another, right? So this simply involves the direct displacement of an atom. You understand? The direct displacement of an atom or groups of atoms by another atom or group of atoms. So I do call this displacement, this substitution reaction, a displacement reaction too. I can also call it a displacement reaction. A displacement reaction, because since we are moving one to add another, so it's definitely a displacement reaction. Okay, let's look at an example. Let's take this for example. Right, so let's assume it's being attacked by, let's say, another element or atom known as Z. Right, so we expect that at the end of this reaction, this stuff should have displaced Y, right? So when such a reaction occurs successfully, we can now say that this is a substitution reaction. So at the end of the process, what will be formed? This is what will be formed here. C, right? Z plus Y. Can you notice something unique? Z has been replaced. Can you see it? Z has been replaced. So this kind of example is known as substitution reaction, and it's used in many parts, is used in many concepts in organic chemistry. For instance, it's used in chlorination of methane. You get? It's used in chlorination, chlorine, from the word chlorine, chlorination of methane. Okay, so how does this thing look like? It's just like the normal methane you are used to, CH4, right? Then you are kind of reacting with it, Cl2, something like this, right? At the end of the process, not at the end, the immediate product form will be CH3Cl, right? CH3Cl plus what? Remember that only one hydrogen was replaced, and there's another one here, so plus HCl. Do you get logic? So that's for chlorination of methane. Also, it is an alkylation of benzene. Alkyl. I've taught you what alkyl is. Example of alkyl. Can you recall? CH3, that is methyl, ethyl, propyl, butyl, and so on and so forth. in case you don't know how to get the formula, like for instance, if I tell you what's the formula for butyl, are you going to know that? So in case you don't know, it's simply CnH2n, right, plus 1. No plus 2, not plus 2. If it's plus 2, it will be alkane, right? If it's OH, it will be alkanol, right? So this is for what? Alkyl. So please do not forget. So let's move on. I told you that it's using alkylation, like this substitution reaction is employed in alkylation of benzene. So benzene is a very, very common compound, common organic compound. You might have heard it several times. So how does the structure look like? It looks like this, right? It looks this way, whereby we have alternating bond, right? Alternating bond. So you should know that at this particular point here is a carbon. At this point also is a carbon. Let me use a different pen so you'll be able to distinguish it. So at this point is a carbon. At this point too is also a carbon. This point a carbon too. This point a carbon. This point a carbon. This point a carbon. So it will definitely form like 4 bonds. It must form 4 bonds. So between here and this particular, let's take this as a case study. It's having 1 bond, 2 bond, 3. So it needs what? 1 more. You get? It needs 1 more. And that's how it is. That 1 more is what hydrogen comes to do. You get? So if you look at the structure, it is going to look something like this. It's going to look like this, right? So this is how it looks like. So the alkylation means that it's reacting with an alkyl, and I'll be making use of chloromethane. So CH3Cl. When it forms, this is the product to give you. Right, your normal structure. So this point will just be replaced by CH3. So I'm replacing the H here by what? CH3. You get? So since H is leaving, and remember that CH3 is what is here. What is left again? Cl. So I'm left with Cl and the H here. So plus HCl. It's as simple as that. So let's talk about another concept, right? Another type of we're done with this. So another type of organic reaction. Let's go to addition reaction. Okay, sorry, let's give some time. I'll need to clean this place. Let's clean this part. Alright, so let's make progress. So now we've talked about the addition, or you can call it displacement reaction. Let's move to the second one, which is addition reaction. So when I say addition reaction, what does that mean? So before I explain scientifically what addition reaction is, let's talk about it. Let's talk about what addition is. So when we say addition, it simply means we're adding something, isn't it? Probably we're adding something we do not have before. You get? So just for instance, 3 plus 2, the 2 increases, right? The 2 increases. Or if I buy you a car, I'm simply adding to the fleet of car you have already, right? So it's similar concept here in chemistry. So when we talk about addition reaction, right, we're actually talking about a reaction, right, that is typical of unsaturated compounds. So when the addition reaction is attributed to unsaturated compounds, So, but the substitution reaction, right, it's more similar or it's more common to saturated compounds. So you might ask, you might be wondering, what does unsaturated compound and what does saturated compound mean, right? Since I've not discussed about it, so let me expatiate on it. Let me talk about it. So saturated means something that is more than enough, right? Unsaturated means something that is not well, like that's not of great quantity. You get? So in organic chemistry, when we talk about unsaturated compound, we're actually talking about the alkene and the alkyne. Right? Why did I say so? Because they have double bond and they have a triple bond. They have more than one bond. You get? So they are simply unsaturated, meaning that they can take up more atom if given. Right? They can take up more atom if given. As we proceed, you will notice, you will discover that we can actually convert this double bond here, these pi bonds. I can actually convert them to sigma bond. You will learn that, right? And it's actually possible because this is an unsaturated compound. It's actually possible because it's an unsaturated compound. So, but what of saturated compounds? What did they even mean by that? Saturated compounds. Alright, it's very simple. It's simply just opposite of what I said here. There is what the main example here is what the alkane, right? That is, it's on normal circumstance, it cannot take additional atoms. So let's say CH3 now, CH4 I mean, right? That is something like this. It can't take up any other atom. This is it. It can't take up any other atom because there won't be space. Remember I told you that carbon can only form 4 bonds, right? It can only form 4 bonds. But for this particular one, it can take up more atom. Do you get that? Because the atom that will be coming will break the pi bond. You understand? Will break the pi bond. Okay, our focus is now on saturated and unsaturated compound. Let's discuss more on addition reaction. So this is a reaction that is typical of unsaturated compound and leads to a decrease in degree of unsaturation. Right? So whenever I'm adding an atom, I'm actually undergoing an addition reaction. I'm actually carrying out an addition reaction. Do you get that? So it involves the addition. This addition reaction involves the addition across an unsaturated bond and gives rise to a less unsaturated or fully saturated product. Now let's see some examples. Let's experiment what we're trying to say. Okay, I'll use ethane for my example now, right? So how can we represent it? So we have C, right? Remember this is CN H2N what only. So from here we can just say C2 H4, isn't it? So 1 2 1 2, something like this. That's the structure of 18. Then one bond to make it complete, isn't it? Alright, so if I wish to break this bond, how am I going to go about it? How did I do it? Okay, I will actually add something. Do you get that? I'll actually add something which are electrophiles. Okay, I'll explain that, right? But for now, I will add some atom, some attacking group. Let me just call it XY. I'll call it XY. So what will be formed is this. See this, right? 1 2 3, 1 2 3. So this pi bond would have broken down, right, to give a sigma bond. Together would have broken down to give a sigma bond. So how is it going to look like? We have H here, we have our X, we have our Y, this and this coming from this up, please don't forget, full up. Okay, so the other ones, the other hydrogen will fill up here, right? You can see that we've actually formed an alkane group, and this is exactly what an addition reaction is all about. So in most of these reactions, actually, unsaturated compounds function as source of electrons, right? So they function as source of electrons, and most of the time I like referring it to what Lewis said about acid and base, right? So this unsaturated compound can also be known as nucleophiles. Why? Because they can act as a source of electron. Let me talk more on electrophile and nucleophile so that you'll be able to understand every concept I'll be explaining. Alright, so electrophile now. Let's talk about electrophile. Right? Okay. It's a very simple concept. Electron, this electron file. You might have heard of phobia and all those rubbish, right? The opposite of that is file, when you like something. So electrophile means that you like electron. A particular compound likes electron. Do you get? And most in life, you actually desire something you don't have, right? So if I have 100 cars in my home, I won't be moved if I see my colleague driving a car, right? Because I have it. So why will I be jealous, or why will I desire more? Do you get? But if I find someone who have an airplane, right, I'll be like, oh, one day I should get that. Do you get? So these electrophiles are actually compounds. They are compounds that are actually electron deficient. So compounds that are electron deficient, right? So electrophiles are compounds that are electron deficient. Now let's link it to what I said about Lewis base and acid. Now, an acid has 3 types of definition, right? So Arrhenius, the first person, defined an acid as a substance which actually dissolves in water to liberate hydrogen ion, or hydrozonium ion, anyone. So the second person is Bronsted Lowry, right? What did he say about an acid? He actually said an acid is a proton donor. Okay, so I'm not particular about the first and second, which is Arrhenius and Lowry. I'm actually particular about the last guy, which is Lewis. The Lewis of a guy. So the way he defined an acid and a base is actually very, very peculiar. It's actually very, very, very unique, right? He actually said that an acid is an electron pair acceptor, right? An acid is an electron pair acceptor. Please take note of it. An acid is an electron pair acceptor. Electron pair acceptor, right? Okay, so that's actually what an acid is according to Lewis. So just like the example I gave, you desire something you don't have, right? You desire something you don't have. So this electrophile we see here can also be regarded as an acid. Is that not true? It can also be regarded as an acid, since electrophile, as I told you, are compounds that are electron deficient and are electron loving, right? So they accept electron. Let's move to the next one, which is nucleophile, right? So yeah, nucleophile. Let's talk about that first, then we'll move on. Nucleophile. It's simple. So this mean from the name, it means nucleus loving, right? Nucleus loving. Nucleus loving. Right? So they desire atoms, right? They tend to be attracted to the nucleus. Do you get that? They tend to be attracted to the nucleus. That means they have electron. Since they don't desire electron, it means that they have an abundance of electron. So abundance of electron. Abundance of electron. Exactly. Okay, so that's for nucleophile now. So just like the opposite, nucleophile are what? Are now base. Nucleophile are now base. So getting back to what I said, this in organic chemistry, unsaturated compounds function as a source of electron. Though not all, I will tell you when they do not function as that. But for I'm referencing alkene and alkyl, right? So these compounds function as a source of electron. That is, they act as nucleophile. Also, they are susceptible to attack by electron deficient species, which are electrophiles. Now, without wasting much of our time, let's move to the next session, which is what? Elimination reaction. Elimination reaction. Alright, so let me talk about what this means. It's very, very simple, right? Elimination is something you can actually relate to. Eliminate, remove. Eliminate, remove. So I like kind of relating to addition reaction, because I feel it's more like an opposite of it. So what did I mean? What is meant by elimination reaction? This is a reaction involving the removal of atoms, right? So involving the removal of atoms, okay, or groups of atoms from two adjacent C atoms to form multiple bonds. So in elimination reaction, multiple bonds are formed, right? All right, so let's take an example, because I believe if you take more of example, it tends to stick. So let's take this example. Alright, are we good? Alright, so when an elimination reaction occurs, two species out of everything will have to leave. Two species out of everything will have to leave. Okay, so I would like to make this very experimentally, to remove one, experimentally actually, right, to remove one halogen and a hydrogen atom, we will have to make use of a compound known as alcoholic KOH. Alcoholic KOH. So when we add alcoholic KOH, a dehydrohalogenation reaction occurs, which is also known as elimination reaction. So what will happen here is that HCl will have to leave. I can't take it from one side, so this particular stuff will be removed from here, and I have to take H from here, or either ways, either this or this, or this or this, right? Either way, anyone I choose to go with. So at the end of the day, this is how it will look like. Right, so one Cl I have left, so I can't remove Cl from here. Here you leave. So this is how it will look like. So since a hydrogen and a halogen left, I can call this a unique name. I can actually call this reaction a very unique name known as dehydrohalogenation reaction. So I can actually call this a very unique name. So over to the fourth one, which is the condensation reaction. What can we say about the condensation reaction? Alright, so this is the reaction in which two or more compounds react to form another compound with the elimination of simple substances like water. So let's give an example. So we know that in the condensation reaction, two organic compounds react to form a single compound, and by default, whenever a condensation reaction occurs, regardless the circumstance, there is always an elimination of a substance. Fortunately, the substances being eliminated are usually simple. It can be water most times. Let me not stress you much. It's usually water, right? So also an example, because when there is an example, you tend to remember more, right? So an example is actually the reaction between ethanol and hydrazine. So ethanol must have two carbon atoms, right? So it will be like this. It looks something like this. I've taught you how I got all this structure at the beginning of the video, right? What of hydrazine? Hydrazine is very, very unique compound. This is the formula, right? This is hydrazine. This is what? This ethanol. Alright. Okay. So when these organic compounds react or condense, they form a very unique compound, right? Known as ethanol hydrazine, which is CH3C, right? This C here, but this O we have to leave. So I will have it this way: NH2, right? These still remain in its place. So what is left? What left? Since one hydrogen is here, right? And one oxygen is here, I mean to say, and two hydrogen are here. It simply means that water is what was liberated, right? Water was what? Liberated. Please take note of it. Alright, the last one, the rearrangement reaction. The rearrangement reaction. Alright, so the rearrangement reaction, this name alone tells it all. Like it talks about everything in it, rearrangement, something when we try to manipulate some settings in this compound, right? So it actually involves the migration of an atom, right, from one site to another, but within the same molecule. It could involve migration of functional group from one point to another. Can we have an example? Let's talk about in rearrangement, the key takeaway is that there is migration. Yeah, so most likely it's a functional group that is migrated. Functional group. I hope you know what my functional group is by now. E.g. it can be OH, CO, OH, CHO, and etc. We'll talk about that more. So let's talk about the example of this rearrangement reaction. right? So I'll take this example, which is CH2Cl, right? The first alkyl group, the second alkyl group, the third alkyl group. So if a rearrangement reaction occurs to this organic compound, what will it be like? It's similar. It's very, very simple to guess the structure, right? Yeah, I'm just using this as an example. It's not always the case this way, right? So this, we have to come here, right? And here we have to go here, right? So let's complete it. Let me just so you can try to know it. So please do not forget. So this is simply a rearrangement reaction, right? A rearrangement reaction. So up next, we will be discussing about the factors affecting organic reactions. Let me clear this space. Alright, so the next part, the next session, which is the next session, which is factors affecting organic reaction, right? My explaining organic reaction will not be complete without this, right? Because we have to know we have to have an idea of when a reaction will not take place, right? And so that we'll be able to avoid it, because sometimes all criteria might be correct. That is, you might have everything in the right proportion, right temperature, right pressure, but still that reaction might not take place, right, due to some factors. Even this factors don't even only affect chemical reaction or organic compound. We are also affected by some factors, right? We are affected by some factors. We can't live in swamp, right, because of some things, right? We can't live in in sea or ocean due to some factors, right? So factors are very important. So basically today there are several factors, but in the course of this video I'll be talking about just two of the factors, right? I'll just be talking about two of the factors, and if need arises, I'll be able to explain more of other factors. So the first one talks about the distribution of electron around the reaction site, right? Around the reaction site. You don't need to disturb yourself much. I'll explain to you what reaction sites mean. So know that the distribution of electron around the reaction site. So this is one of the factors that affects organic reaction. The second is the nature and the size of the atom. The nature and the size. Right? Nature and size of the atom surrounding the reaction site. So nature and size of atom around reaction site, right? So that's that for that. So what do I mean by this? Okay, I will explain in full details. There are some things I want you to note first, right? A terminology which is known as inductive effect. So I'll talk about inductive effects. I'll also talk about mesomeric effects, and lastly I'll talk about steric effects, right? This is kind of establishing the concept to make you understand what I mean, right? Okay, so for the first one, which is inductive effects. Alright, good. So for the inductive effect, this is actually a polarizing effect, but a permanent polarizing effect. So we know from inductive effect that this is a permanent polarizing effect. So polarizing from the right polarization means it's forming positive and negative end. It's nothing hard, right? A permanent polarizing effect in single bond. So this is peculiar to single bond. To single bond, right? It's peculiar to single bond. So the effect is caused initially by covalent bond between atoms of different electronegativity, right? So whenever we have adjacent atom that are of different electronegativity value, actually an inductive effect occurs, most especially when it is in a single bond. Do you get that? So the effect is actually brought about by an equal sharing of electron. Let me give you an example. So let's assume we have a carbon attached to let's say chlorine, right? Attached to chlorine. This is more electronegative than this. So this is actually what? Electron. Is that not true? This is actually electron. Okay, so if on a normal circumstance, where will the electron be drawn to? Will it be drawn to carbon or will it be drawn to chlorine? Can you guess that? It will be drawn to what? Chlorine. And why is it so? Because chlorine has higher electronegativity value. It has high electronegativity value. Do you get that? So what will let me just draw a very more example so you can be able to. Okay, just this the expansion of this. Okay, so if this is drawing more of the electron, it's become what? Partially negative, right? And this was partially what? Positive. Partially negative, partially positive. So the same effect goes through these atoms. The same effect goes through these what? Atoms. So but the thing is that this polarizing effect, or let's just say inductive effect, tends to be insignificant beyond 2 carbon. So it can only be significant, the effect can only be felt between this carbon and this carbon. You hardly find the inductive effect on the 3rd carbon, right? Okay, so there are actually two types of inductive effects, right? There are actually what? 2 types. And what are they? It's actually, the first one is the negative effect, negative inductant effect, right? And the second one is positive inductance effect, right? It's very simple to understand the negative and the positive inductance effect, right? So but now when the group attached to the withdrawing electron, right? When the group attached withdraw electron, so when the group, this particular group is what's attached to this now, normal, right? So when this group attached here withdraws electron with respect to the carbon, with respect to this carbon, you get the effect is termed a negative inductance effect. It's termed the negative what? Inductance effect. And when this group is actually donating electron, do you get? When the group is actually donating electron, the effect is known as positive inductance effect. Positive inductance effect. Do you get that? And most of the time we witness this type of effect whenever an alkyl group is attached. I hope you know by now what an alkyl group is usually represented by R. So whenever an alkyl group is attached, right? Okay, now it's actually important you know some example of atoms or group of atoms that cause negative effects. Okay, the first one is COOH, which is the carboxylic group, right? The second one is COOR, which is known as the ester, the functional group ester, right? Nitro also, NO2, is actually an electron withdrawing group, right? Halogen too. just like what I explained there. Halogen is also an electron withdrawing group. So the halogen, the whole of halogen, so halo, I'll just write halo, Cl. So the whole of halogen group are actually withdrawing group. Also cyano, which is Cn, is also an electron withdrawing group. But for positive effects, it's normally an alkyl group. It's normally an alkyl group. Okay, so what are the other terminologies you have to think of? The mesomeric effect. The mesomeric effect. Okay, so what is meant by this? Now, in inductive effect, right? In inductive effect, I told you that it involves single bond. It involves a single bond. But in mesomeric effect, actually it deals with two bonds. It deals with double bond most of the time, right? It deals with double bond. Now, there is actually a shift, right? There is actually a shift of pi electrons in multiple bonds toward the more electronegative atom. Together. So whenever there is a shift of pi electron in multiple bonds towards the more electronegative atom, it's actually referred to as what? A mesomeric effect. It's actually referred to as a mesomeric effect. Now, it is similar to inductive effect in that there is actually shifting of electron, right? There's actually shifting of electron, but it differs in something very, very peculiar. It differs in something very, very peculiar, but we'll get to know what it differs in. So this mesomeric effect is carbon to carbonyl group, or carbonyl compounds. I hope you understand what we mean by carbonyl compounds. Okay, so whenever you see carbonyl compound, we're actually talking about compounds that have this kind of group, this group in it. Example: alkanal, alkanone, carboxylic acid, right, and so on and so forth. You understand? So in this kind of compound, all these compound or homologous series that I actually mentioned now, there is a shift of pi electrons. There is a shift of pi electrons towards the hydrogen, towards this hydrogen, right? So now, I told you earlier on that mesomeric effect and inductive effect are way similar, are very similar. But the difference between inductive and mesomeric effect is that there is no visible shift of electron in inductive, right? There is no visible shift of this electron in inductive, but there is a visible shift. There is a visible shift, right? There is a visible shift. There's a visible shift. Please take note of it. There is a visible shift in mesomeric effect, and it is due to the pi electron. It is due to the pi electron. Now let's talk about the next one, which is the steric effect. The steric effect. The steric effect, right? So this is the effect due to the size of group surrounding the reaction site. So it's due to the size of group. How to speak about steric effect? It's due to the size of group surrounding the reaction site of the molecule. So this occurs when certain atoms alter, or in some cases completely prevent a reaction from taking place despite favorable conditions. This effect is known as steric hindrance. Steric hindrance. Okay, and particularly effective when the reaction site is crowded with bulky groups. So this is what it means. This is what it means. Like methane, something like this. This is methane, right? Steric hindrance cannot have effects here. Reason because these are not bulky group. They are not. Now let me tell you what a bulky group will look like. So let's assume we have another compound which is C and then CH and then let's say CH3, right? Then this one C2H5, this one C3H7, this CH3. This is the bulky group. Can you just imagine? Let's look at this now. This is what bulky group. So steric hindrance will have an effect here, right? So as I move on, you'll be able to understand more about the steric effect. And lastly, I would like to talk about a very, very important terminology, right? Known as homolytic fission, and heterolytic fission. Alright, so this is very, very simple to understand. Homo means the same. Lytic means breakage or breaking. Right? Fission is something you should understand. Hetero means hetero. Please correct the spelling. Hetero. It means different. Right? Hetero. When I say hetero, I mean something being different. Right? Okay. So what does this mean? Heterolytic fission. When I say heterolytic fission, what did I really mean? Homolytic fission. I mean, what did I really mean? So homolytic fission takes place between atoms of similar electronegativity. Right? This is fission in which the electron pair, right, is shared equally between the two atoms sharing the bond. So electron pair in this part are shared equally. Electron pair are shared equally in homolytic fission, right? Why are they shared equally? Because of the same electronegativity value. So they are shared equally because of what? The same electronegativity value. So most of the time they are actually the same type of element, right? Let's say something like Cl2 for instance, right? Now we know that we expect something very, very unique here to happen. If this should undergo a homolytic or a fission generally, it will be a homolytic fission. Why? Because it will form Cl and Cl, right? It will form Cl and Cl, which is actually of the same electronegativity, which is the same electronegativity value, right? So now between Cl and Cl, there are actually two electrons here. In homolytic fission, they will have what? One electron attached to themselves. They will have one electron attached to themselves. Do you get that? They will have one electron attached to themselves. They will have one electron attached to themselves. So this part, this kind of I'll not say an ion, right? But this kind of atom is known as a radical. Do you get? Is known as a radical. So homolytic fission is also known as radical fission, right? Radical fission. Why? Because radicals are produced. Because radicals are produced. Okay? Because radicals are produced. So chemical reaction involving homolytic fission are known as free radical reaction, whichever I said. Homolytic fission also requires large amount of energy. Large amount of energy are required for homolytic fission. Therefore, it takes place in very high temperature or under UV light. So the next one, heterolytic fission. All right, let's make progress. So over to the next one, which is heterolytic fission. Right, so let's talk about this. Okay, so for heterolytic, I told you that it's something very easy to understand, right? Very easy to understand. And hetero means something different. Hetero means something different, and lytic, as usual, means breaking. So heterolytic fission takes place between atoms of different electronegativity value. It involves the transfer of electron pair to the more electronegative atom, leading to the formation of charged species or ion. So now here's what happens in heterolytic fission. There is difference in electronegativity value, right? So that's one thing peculiar about heterolytic fission. Not only that, there is a transfer of electron. So there's a transfer of electron from the less electronegativity one to the more electronegativity one. That means that electron pair are not shared equally in what heterolytic fission. And just like what we've known before now, whenever there is an unequal sharing of electron, what really happens? There is positive and negative charge are formed. Positive and negative charge are formed. So what's this similar to? If positive and negative charge are formed, let's say we're talking about a particular compound or a particular atom, or a particular molecule known as AB, right? And let's say this is more electronegativity than this. So this is what will really happen. This A, then B. They just take the two electron pair, right? So this becomes positive and this becomes negative since it has one more electron. Do you understand that? So what is this similar to? This looks like an ion, a positive ion, right, and a negative ion. You get? So it's kind of what is similar or peculiar about heterolytic fission. So this heterolytic fission is also known as polar, right? The heterolytic fission is also known as polar fission, right? Polar fission or ionic fission. Why is it known as that? Because ions are formed. So it's known as ionic fission or polar fission. And by now you should know why it's called that, because what ionic products are formed. So that's all the terminologies that are left to talk about. So let me kind of run through what I said about the factors affecting organic reaction, right? Factors affecting organic reaction. So here's it. We have a distribution of electron around the reaction site. So depending on where the electron is, right, I can't really visualize it now, but depending on where the electron is, it also determines how fast or how slow the reaction will be. Also the nature of the atom around the reaction site. You can look at what I did in that steric hindrance, something like that. It's similar to this, right? So when we have a very bulky groups of atoms around the reaction site, right, the reaction tends to be slow. Generally the reaction tends to be slow. Okay, so that's all you need to know about the basics of organic reaction. Now let's forge ahead to the simplest homologous series, right, which is what? Alkane. So follow me as we dive into alkane and unravel it. Alright, so welcome back. In this section, I'll be talking more on alkane. Right? But before I continue, right, I would like to talk about hydrocarbons. I would like to talk about hydrocarbons as it will help. It will serve as a guidance, right, to all that we're discussing as we move along. So first of all, what is hydrocarbon? When we say hydrocarbon, what do we mean by hydrocarbon? Okay, the name says it all actually, right? It means a particular compound or a particular organic compound that has two components, which are hydrogen and carbon only. Do you get? Okay, so a hydrocarbon is defined as an organic compound that consists or comprises hydrogen and carbon only. Hydrogen and carbon only. Alright, so a hydrocarbon can be divided into two main parts based on the structure, into two main categories, right? What are they? They are called aliphatic and aromatic. Aliphatic and aromatic. So that's for hydrocarbon now. Do you get? So they are divided into two parts, which is aliphatic and aromatic. Now this aliphatic is further divided into other parts. You get? Which is alkane, sorry, mistake. So which is alkane, alkyne, right? And what? Alicyclic. Okay, so let me just spell it well, sorry. Alicyclic. Okay, so I'm sure you're familiar with these three guys, but the alicyclic is also very easy to understand. It comes from two words which are merged together: cyclic, aliphatic. You get that? So this last part, which is alicyclic, talks about the cyclic form of alkene, the cyclic form of alkene, the cyclic form of alkyne, right? So that's exactly what it's talking about. You understand? Okay, so that's that for that. We'll be starting from this alkane. That is the first one. This video covered, but in subsequent video I will now talk more on alkene, alkyne, alicyclic, aromatic, and on and on and on, right? So, but that's not all. We still have to talk about something very, very important, and that's petroleum. And that's petroleum actually, right? That's petroleum. Okay, so like petroleum is something that you come across very well, right? It's very important in the sense that all these organic compounds, most of these in short, hydrocarbons itself are produced from petroleum. Most of them are produced from petroleum. So it's actually important that we know how it came about. I guess the origin of this petroleum. So petroleum is considered to rise from dead marine organisms, right? So according to scientists, they said that petroleum was derived or came about, right, from dead marine organisms. I get it, which were buried under rock sediments some 100 million years ago. So now these dead marine organisms are deep down in the ocean, right? So the effect of pressure and temperature is actually very, very high on them. Therefore, it led to the decomposition and maturation, right? So it led to the decomposition. The effect of the temperature and pressure led to decomposition and maturation of the deposit, the dead organism. You get that? He dead organism. So now we know how it came about. It's still not profitable to us. We have to know, okay, what can we even get from this guy? What can we even get from petroleum? Now, in order to extract the content of petroleum, we have to use a particular separating technique known as fractional distillation, right? Fractional distillation. Now, whenever we use fractional distillation in chemistry, whenever we use fractional distillation, it simply means that the constituent, or what we're trying to separate, consists of several components of very close boiling point. I guess of very close boiling point. So that's why we use a fractional distillation. So when we fractionate petroleum, for instance, there are several components you get. One of them is gas fraction. Gas fractions. Others are gasoline, kerosene, light gas oil, heavy gas oil, lubricant, distillation residue, etc. But my focus here will be on gas fraction because it's something we can relate, not only relate, it pertains to what I'm talking about. It pertains to the topic I'll be discussing. Do you get? So the gas fraction actually consists of all hydrocarbons from C1 to C5. Therefore, your methane are under gas fraction, your ethane are under gas fraction, propane down to pentane are under what? Gas fractions. Do you understand that? Even your natural gas are under what? Gas fractions too. That even reminds me. Natural gas, what does it comprises of? Natural gas, if you don't know, please take note. Natural gas comprises of methane. Yeah, methane and ethane. That's what natural gas comprises of. So since from methane down to pentane are under gas fraction, therefore our cooking gas, the one you use at home, right, falls under this, because the bottle gas or your cooking gas consists of mainly two hydrocarbons, which are propane and butane. So your cooking gas, the one you use at home, comprises mainly of propane and butane, right? So that's that for that. Now let's get into business. Nice. So let's talk about alkane now. Alkane in details. So this is a very unique compound, right? It's a very unique compound. Why did I say so? It's kind of not even reactive at all. Do you get? It's kind of not reactive. In short, that's the reason it was given a particular name known as paraffin. It was given a very unique name known as paraffin. So now, what does this paraffin mean? Paraffin originated from a Latin word. In short, two Latin words, right, which are parum and affins. Parum and affins. Do you get? So this parum means affinity, enough. This parum means enough. Why affins means what? Affinity. So it's clear now that paraffin mean enough affinity. So why would they even call it such a funny name? It's funny now. How do you say something is enough affinity? Now follow me. Remember that alkane, as I told you earlier on, is actually a saturated compound. It's saturated. It's saturated. Therefore, it hardly undergo chemical reactions. You get? It hardly undergo chemical reactions. For example, it does not react with acid. Even H2SO4. It does not react with H2SO4 at ordinary temperature. Do you get that? Even oxidizing agent, the strongest being KMNO4, like oxygen, it does not react. Do you get that? Under ordinary condition, right? Alkane does not even react with reducing agents such as hydrogen. Even in the presence of what? Catalyst, it does not react. And that's because of it's being saturated. Do you understand that? It's being saturated. So there is literally no bond to break. There is literally no bond that the atom being added will break. But if we were to talk about the alkene, for instance, now we will say, okay, since we're talking about the alkene, then it will break the pi bond. But this one, no pi bond, only what? Sigma bond. Do you get that? So that's the reason it's saturated. It's called what? Paraffin, and which means enough affinity. Now, knowing that is not all. You also need to know the general formula of alkane, right? If you know the general formula of alkane, I can tell you can know almost all the homologous series, all the examples. Do you get? So what's the general formula? It's simple to remember: Cn H2n plus 2. I've written this before, right? So Cn H2n plus 2. The n ranging from 1 to greater than 1. Do you get? So from 100, as long as you can go. Do you get? As long as you can go. And one thing peculiar I forgot to mention under hydrocarbons. One thing peculiar is that all hydrocarbons, when they react with oxygen, excess oxygen to be precise, they form CO2, right? So when hydrocarbon reacts with oxygen, they form CO2 plus water. Excess, it has to be in excess. But when there is not enough oxygen, what is formed is actually carbon monoxide, or what you know as carbon dioxide, right? Carbon dioxide and H2O. Carbon dioxide and H2O. Now, I would like to talk about something else, right? Talking about something else, which pertains to petroleum generally, right? And it's actually called knocking. Now, this is not like banging on the door. Nope, it's not banging on the door. It's actually a very unique occurrence that happens in engine, right? That happens in engine. So what does this knocking talks about? Now, petrol. Not all petrol have the same quality, right? There are some petrol that has higher quality than others. So what really happens when we have petrol, when we buy petrol of very, very low quality? To get that, when we buy very low quality, what really happens compared to another person buying a petrol of higher quality? Now, when we continually use petrol of higher quality, with time our engine starts developing fault. Why did it start developing fault? This low petrol find it difficult, it hardly combusts, right? Find it difficult to burn. Therefore, whenever it burns, because definitely it will, whenever it burns, it leaves residue. It leaves some particle in the internal combustion of this engine, and with time you hear some noise. This noise are damaging noise to the what? To the engine. Do you get it? But one which a particular car which uses good petrol hardly develops such a fault. But what if we did not want to buy faulty or low petrol on purpose? How can we correct this defect? It's simple. By adding a particular compound known as C2 tetraethyllead. You understand? So this is the, let me just write it, tetraethyllead. I guess it. So tetraethyllead, right? By adding tetraethyllead to the petroleum, to the tank, I guess, will help improve our fuel, will help improve the state of our engine. Did you get that? But there is a problem. That is the sulfur content of petrol. Yes, the sulfur content of petrol is also deadly. In short, let me just tell you a fact. Nigerian petrol is one of the most sought petroleum petrol in the whole world. Why? Because of its low sulfur content. Sulfur is actually detrimental, or an undesirable component in petrol. Do you get? Because it actually affects the smooth combustion of petrol in the internal combustion energies in the internal combustion engine. As it deactivates this compound, it deactivates this stuff. It deactivates this guy. So sulfur deactivates what? The tetraethyl lead. And when scientists find out that, since the sulfur is causing this problem most of the time, they have to develop a process whereby they remove it during refining, when they are refining this petroleum. You understand? But it's an additional cost. It's an additional cost, and all those stuff. You have to pay workers. It adds more money to the cost for production. It adds more money to the cost of production. Now, since we know that bad fuel or low quality fuel is very very bad, right? But how do we even know that a particular fuel is bad? For instance, if we brought it to the laboratory. Now, the more branched a particular organic compound, or the more branched a petroleum is, the higher its octane rating, right? Octane rating is actually a scale we use in determining the quality of a petrol. In this scale, the highest petrol will be 2,2,4 trimethylpentane. So on this octane scale, or this octane rating, this particular compound, also known as isooctane, sorry, I made a mistake. Isooctane, right? Is what? 100. While the lowest is heptane, which is 0. So when we examine a particular organic compound, or the petrol to be precise, in the laboratory, and find out that we're getting, let's say, probably we're getting let's say heptane or 2-methylhexane, something like that, right? 2-methylhexane. You know that this petrol is not that good, I guess it. So we are actually comparing it to these two compounds generally. Now, I said that we can also call 2,2,4 trimethylpentane isooctane. Why is this so? Why am I calling that? All right, follow me closely. So 2,2,4 trimethylpentane is also called isooctane. Now let's draw the structure, so I'll be able to explain to you why we can also call it isooctane. Okay, so from here, let's draw it. 1, 2, 3, 4, 5. But if you don't know how I arrive at this structure, right, where I'm actually writing out 5 carbon, you don't need to worry yourself. I'll explain it in subsequent sessions. Right, so this something like this. Now 2, 2 methyl. So 1, 2. Wow, I'll see here. Wow, I'll see here too. Wow, I'll see here. So 1, 2, 1, 2, 3, 4. Wow, I'll see here too. Isn't it? I don't need to write all these ones here because they are all hydrogen atom. All hydrogen atom will be placed here. If you take time for me to write it, let's try to save time. Alright, so this particular guy is methyl, this is methyl, and this is what? Methyl. That's why we have tri-methyl. Now, why do we call it isooctane? This iso here means isomer. So what I'm trying to say is isomer of octane. It's as simple as that. Isomer of octane. So the thing here, let's count the number of carbon, like every single one of them. This is 5, 6, 7, 8. Do you get that? So which is what? Octane. 8 is octane now. Is that not true? So you can say what? Isomer of octane. When we find the isomer of octane, one of them will definitely be what? 2,2,4 trimethyl pentane. Okay, that's that for that. Let's talk about the preparation of alkane. The preparation of alkane. How can we produce this? How can we produce this guy? Probably in the laboratory or wheresoever. So now, before we found out that it's actually very possible to produce this alkane in a unique way. Before then, we are actually extracting some of the alkane from petroleum products, from petroleum distillate. Do you get that? And to be frank with you, like, is a fact that from methane, like alkane from methane through N-pentane and isooctane and isopentane can be obtained in pure form from fractional distillation of petroleum and natural gas. So if we want to obtain, if we want to extract or produce methane, if I'm feeling reluctant to use the laboratory procedure, I can actually extract it from petroleum products, from petroleum and natural gas, right? It's obvious now, natural gas comprise methane and ethane, so you should know. So above methane, right, the number of isomer of each homologue right, becomes so large, and the boiling point difference becomes so small. So just imagine if we're having something like 15 degrees Celsius and the next isomer is 16 degrees Celsius. That's very, very bad. It's very, very hard for us to separate it very well. There will be some lags. There will be some lags. So it's not feasible to produce any methane, any alkane above isopentane through petroleum. So we now have to devise a methodology which we are going to be using, and I'll be taking you through that. Now, the first method to produce it, apart from through the petroleum method, is actually hydrogenation of alkene. Please take note of alkene, right? So alkene have what? They have double bond. Please take note. So how can we produce it from alkene? It's very, very simple. Now, the general formula for alkene is CnH2n, right, of alkene. So when we react it with hydrogen, remember, we can't just react it anyhow. Catalysts have to be present. Most likely we use platinum. Right? So when we add hydrogen here, this is hydrogen, this is also hydrogen. What do you think will be formed? It will form CnH2n plus 2. This added 2 here. Do you get that? Now? It's actually very straightforward. So this is the most important method for preparation of alkane. With alkane reacting with hydrogen under slight pressure and in the presence of catalyst, the alkane is converted smoothly and quantitatively into alkane of the same carbon skeleton. Another method which we can use apart from hydrogenation of alkane is actually reduction of alkyl halide. Okay, so how is this so? Now we can pass through several routes to get this job done. The first is hydrolysis of Grignard reagent. Hydrolysis of Grignard reagent. Okay, first of all, I'd like to explain to you what Grignard reagent means so you'll be able to flow better. Right, so Grignard reagent is kind of a reagent, or let's say an organometallic compound, right, formed from the reaction of magnesium, with alkyl halide, so plus alkyl halide, indicate in the presence of dry ether. Take note of dry. So in presence of dry ether, right? So let me tell you how this is formed. So this is magnesium, right? An example of alkyl halide can be CH3 halide. Let's just choose anything. Let's go with I. That is iodine, something like that. So it's just from in the presence of ether. So it will form CH3 MgI, right? So this stuff you see here is now what is known as Grignard reagent. So the formula to getting this is simple: Mg plus Rx. This is alkyl, this is halogen, to form RMGX. So along the course of this video, I might be using only this one because it's not a must. It's not stress myself writing this stuff, right? I can just write this and represent it. So when we react Grignard reagents with water, ticket, or react Grignard reagents, so when we have RMGX plus water, I don't write it as H2O, like, so you just permit me to write it this way so that you guys will be able to understand HOH. Let's just write it this way, right? So let's write it this way. So this R will have to react with one of these hydrogen. Let me pick this. Let me pick this stuff. So it will form RH plus MgOH, right? What's left? X. So this is an alkane. Is that not true? This is an alkane. Remember that before now I told you that the formula for alkyl is what? CnH2n plus 1. Hope you know. So this is an alkyl group. When we add one hydrogen, it becomes what? It becomes 2. Can you see it? And what is that? An alkane. So please take note of that. Okay, so another method of preparing alkane is through the use of, or through the reduction of metal and acid, right? Through the reduction of metal and acid. So we are reducing alkyl halides, right? We're reducing alkyl halide with metal and acid together, right? So how would this look like? So the B, reduction of metal and acid, right? So let's write the formula. Rx is for alkyl halide plus zinc plus H2 plus, right? So instead of me writing a particular acid, let's say HCl, HCl, if I just write the ion, it's still the same thing. You understand? So when we react it, what does it form? It forms RH plus zinc 2 plus. Now why am I writing zinc 2 plus? Remember I said I can write Cl here. The Cl will have to form this, will form something like to form a salt, right? But I don't want to, since I didn't write any anion here, it's better I leave it this way, right? So Zn2 plus, right? plus x, that is, the x is coming from here, so the x is coming from here, just take note. Yeah, minus, right? So this is actually the formula for it. Let me give you a good example, because I think if I give you an example, you'll be able to remember it more. Now look at this example. Okay. So let's in short, pause this video, go offline, just pause the video and try to get it using this methodology here. Try to get it, so because the more you practice, the more you understand organic chemistry. So let's try it. So from here, I'll use this method so you understand it. This R, so this part is the R, that is the alkyl group. Nice. So what really happened, I'll just replace this Br with H. It's as simple as that. Let's do that. Let's do it. So let me change the pen, sorry. So we have CH3, CH2, CH3, right? So I need to write 3. What I write? CS3. Good. So this is what? H. Are you fine? So since this is forming H, so and the other product that we form will be ZnBr. Will it just BR? No, BR2, right? So that was the other product we formed. To get that was the other product we formed. So that's that for that. Another method we can use, yeah, those are the methods we can use in preparation of alkane. To get those are the methods we can use in preparation of alkane. So let's talk about the chemical reactions that alkane generally undergo. All right, welcome back. So let's move on to the second session, which is the chemical reaction that this alkane undergo. Right? Basically, there are several reactions that it undergo, but some of them are not that important. Right? So I'll be talking about just the 3 main important ones. The 3 main important ones you should take note of. Right? And the first one is oxidation reaction, or combustion, whichever one you wish to call it. Right? So like I said before, all hydrocarbons are attacked by oxygen at elevated temperature, and if oxygen is in excess, complete combustion occurs to produce carbon dioxide and water. Now, how does this reaction occur? Now, let's use the first member, which is methane, which is CH4, right? So now, plus excess oxygen, let's say 2 here. We'll balance it when we are through. So normally, in the presence of excess oxygen, it produces CO2 and water. No dispute about this. And lastly, energy in form of heat. I hope you get energy in form of heat. So let's balance this. How is it going to be balanced? C here, 2, 2, right? 4, 2. So I'll have to put 2 here, right? Okay, this 2 now. I have to add 2 here for it to be balanced. I hope you are following. Good. So this is a balanced reaction now. So if the heat evolved in this process, right, which I can call the heat of combustion, right? The heat of combustion is the measure of the amount of energy stored in these bonds, in the sigma bond. It's the measure of energy stored in the sigma bond, because what it's actually doing is that these bonds here are actually broken. These bonds here are actually broken by the addition of oxygen or by the reaction of oxygen. So now, how can I know the value of this energy? How can I know the value of this energy? It's simple. By the use of calorimeter, or by calculating the bond energy of this sigma bond, right? I will talk about that when we were talking about energetics and all that. So we can actually calculate it accurately, the amount of energy released, right? But for this kind of reaction, it's a constant. The amount of energy released here is 212.8. Yeah, 212.8 kilocalorie. Cal means calories, kilocalorie. Now let's talk about halogenation, the second part of it. The second type of chemical reaction undergo by alkane, which is halogenation of alkane. Alright, so the name says it all. The name says it all, that when we are actually trying to convert a generic alkane, right, to having or to acquiring a halogen, it might be chlorine, it might be bromine, or whatever. So but this kind of reaction must undergo or takes place under the influence of ultraviolet light, right? This kind of reaction takes place under the influence of ultraviolet light. So under the influence of UV light. Or if UV light is not present, we can actually use or 250 degrees Celsius to 400 degrees Celsius of heat by adding it, right? So mostly the halogen that reacts with alkane are mainly chlorine and bromine. So chlorine converts alkane to chloroalkane, or can just say alkyl chlorides, right? And bromine converts alkane to bromoalkane, right? Or I can just say alkyl bromide, right? So whenever such a reaction takes place, I'm going to represent it, so don't worry. So whenever such a reaction takes place, an equivalent amount of HCl or hydrogen bromide is formed at the same time. Okay, so depending on which oxygen is replaced, any of the number of isomeric products can be formed. Now let me tell you what I mean. Now, a whole lot of products can be formed from halogenation of alkane. A whole lot. Now let's take a look at it. Okay, let's say CH4. Let me use the simplest one. I don't want to make things complicated. CH4 plus chlorine. Okay, so what is formed? We can use UV light. I hope you know. We can use UV light. And whenever we're using UV light, we can just add 25 degrees Celsius, right? The heat of 25 degrees Celsius to make it faster. So one of the hydrogen here will be replaced. Do you get? One of the hydrogen here will be replaced. So we'll have CH3Cl plus. Remember, one hydrogen is leaving. This Cl. So HCl. Do you get that? HCl. And on like that. And on like. If chlorine is still present, then this one will later form CH2Cl2 CHCl3, right? And on like that. So it's actually very straightforward. It's a very simple procedure, right? Okay, or let's just talk about it, because there is something that I need you to take note of. Now, this particular guy, right? This particular guy is known as chloroform. You get known as chloroform, and it's very important in chemistry. Chloroform. So it's actually very important in chemistry, or the medical world, to be specific. It's very important in medical world. Reason because it can be used as anesthetic, right? It can be used as anesthetic. Now, if we still react chlorine with this particular compound here, what we formed will actually form CCl4. This is known as carbon tetrachloride. So carbon tetrachloride is used as a non-flammable cleaning agent, right? And also as a fluid in certain fire extinguishers, right? So please do not forget what I said. This is chloroform. It is as anesthetic. Anesthetic. Are we good? So all of this, that is carbon tetrachloride. Carbon tetrachloride. I following carbon tetrachloride. Okay, so we are good with that, and this is fire extinguishers or non-flammable cleaning agents. So do not forget. So now let's talk about this mechanism of halogenation. Since it's a very, very important process, there are actually some steps that undergo or that must take place before halogenation actually occurs, right? Before halogenation actually what occurs. Let's move on. All right, so let's move to the mechanism of the mechanism of halogenation. You get, since it's a very, very important concept, understanding the basics of it is also advisable. Alright, so halogenation, right? Halogenation of alkane works or proceed by a chain reaction. So one fact we know is that it works or proceed by a chain reaction. By a chain reaction. So what does this chain reaction mean? Alright, so it's just like the concept of chain. That is, one is connecting to the other, one is connecting to the other. Now, in chain reaction in organic chemistry, we mean that one particular step initiates other steps, right? It's just like something automatic. Now, let me give you a very, very good example you can relate with. Let's assume we have dominoes, right? Dominoes of this kind. Yeah, something like this. If I were to heat this stuff to make it look in this direction, to make it look like this, what do you think will happen to all these ones? They will definitely fall down, isn't it? So that's just like what? A chain reaction. Now, a chain reaction in this mechanism of halogenation can also be likened or can also be called radical mechanism. And I'll tell you why it's known as radical mechanism. Now, I'm very sure you understand what I mean by radical, right? Radical are very, very reactive species, right? They're very, very reactive species. So for this reaction to keep on going, definitely there should be something that acts as catalyst. There should be something that will help, right? Will help make this reaction ongoing. Will continue the process of this reaction. And that's the function of the radical. You get the radical. So now let's look at how it goes. There are actually basically 3 steps you have to take note of. Now, step 1 is called chain initiation step. The chain initiation step. So how does this work? Let's say we have something like this, right? And we want to form a product. Now, a homolytic fission will occur here, right? Homolytic fission will occur here in the presence of UV light, or at a temperature of 250 degrees Celsius to 400 degrees Celsius. You get, so since homolytic fission will form here, this ought to be formed something like this. We can just say 2x, right? Something like this. It's still the same thing. So this is the first step. This is the first step. Now, what is the second step? Step 2. What's it called? It's actually known as chain propagation. Chain propagation steps. Alright, so how does this work? How does this chain propagation step? It's just like the continuation of the chain reaction. Now, we have radical presence in this reacting system. Therefore, it will keep on going until it finds a place to rest. Now, if it's going how does it go? Like, what are the products that we formed? Remember, we are reacting it with alkane. Alkane can be represented like this. I've told you, I'm sorry, XRH. Alkane can be represented like this. Why can it represent like this? This is an alkyl, right? Which is CnH2n plus 1, right? This H, so it makes it CH2n plus 2. So this is an alkane, right? So if this X was to come here, so we have something like X, given what? HX plus R, forming another radical. This radical now, we now come and what? React to this stuff, continuing the process. So one particular reaction helps the other. So it looks like this. So we don't need to be adding heat or increasing the temperature. No. Just the initiation step is enough to carry it on. So it's now, sorry, not this. It will be this. Please take note. This is not here. Okay. So forming what? Rx plus X plus radical. Rx plus radical. So this step continues, in short, forever, except the third step occur. And the third step is known as the chain terminating step. The third step is known as the chain terminating step. You get the third step is known as the chain terminating step. If this guy remain in this system, this chemical system, it will never stop. It will never stop except the reactant depreciates or finishes. Now, if we want to stop it, we have to ensure a reaction like this occurs. We have to ensure that a reaction like this occurs. And what's the reaction? Something like X radical reacting with another X radical to give X2, or R radical reacting with L radical, right, to give R or 2R. Let's just put it as 2R. Now, what if the R radical and X radical are not enough to cancel out each other? What will happen? The R can also react with X to form Rx. So if this particular reaction occurs, then the steps finishes, right? The step finishes totally. Now, the last type of chemical reaction that alkanes are capable of undergoing is called sulfonation reaction. It's called sulfonation reaction. Okay, so now from the word sulfur, so sulfonation reaction. So we can know that when we talk about sulfonation reaction, we are actually talking about something that has to do with sulfur, right? That has to do with sulfur. Remember that I told you that alkane are known as paraffin. That is, they are very stable, right? They hardly react with most compounds such as H2SO4 and all that. But under certain conditions, they can also react, right? Under certain conditions, they can react. For instance, under the sulfonation of alkane, we'll get to know that alkane can actually react with fuming, H2SO4, right? This fuming H2SO4 is not like the normal H2SO4 you know, though it's still the basics of H2SO4, but it's a little bit different in that it's known as oleum. It is known as oleum. And what's the formula for oleum? Now, oleum is simply comprises of like H2SO4 plus SO3. Therefore, the formula for oleum is H2S2O7. You get? So when alkane reacts with oleum, or we can just say fuming H2SO4, a reaction undergoes, right? It forms alkane sulfonic acid. It forms what? Alkane sulfonic acid. Now, how does this go, or how does it proceed? Now, I would not like to use my abbreviation to explain this. I'll use a normal formula known as 2-methylpropane, right? 2-methylpropane. So let's draw it. it will have 3 normal, 2 methyl, so it has something like this, right? So it has something like this, something like this, so something like this. So it's still the same thing, right? So plus, let me restructure this so you'll be able to understand it well. Let me restructure this. So we have C H CH3 CH3 CH3. So they are basically the same thing. So when they react with oleo, which is H2S2O7, what does it form? It's simple. Now remember that these comprise of this. I hope you know that it comprises of that. So this is very reactive. This SO3 you see here is very reactive, and that's what will come and partner with this guy. That's what will come and partner with that guy. And when it happens that way, we say that a sulfonic acid has been formed. So what's the formula for this sulfonic acid of the thing? CH3 CH3 CH3, and here will be SO3 and H. It's as simple as that. So now we've come to the end of everything you need to know about alkane. Yes, but the preparation and everything, that's just it. You get. So the next session we'll be talking about, we'll try to solve some questions basically, right? Like yeah, we'll solve questions basically, most especially naming of all these compounds, alkane compounds. So that reminds me, if you are new here, please consider subscribing to this channel, right? So consider subscribing to this channel, and also if you would like to get an exclusive class, right? Post UTME classes are currently ongoing, or premium classes are ongoing for a very affordable amount, of 5,000 naira. And if you're interested, just comment in the section that you're interested in the premium class, drop your contact number or your email address. We will contact you, our team will contact you perfectly. We have expert tutors that will train you to become the best version of yourself. Apart from that, you don't just learn from Gallant Tutors, we also build you to have a superior mindset, right? So now let's move to this the question part of this video, so that at least you'll be able to have a grasp of the basic of organic chemistry. Let's move. All right, so to the final part of this video, I strongly believe that if you are at this point of the video, and if you followed me closely, paid rapt attention to my teachings, then by now at least you should know the basics in details, right? Okay, we've talked about hybridization, preparation of alkane, some of the chemical reaction that alkane actually undergo. Well, that's not all. Those are important, but these are more important, right? Which is now the nomenclature of alkane, so that whenever you see a compound, especially of homologous series alkane, then you should not panic, right? You should not panic. You should just go straight, pick your correct option, and move on. So I will try my best possible to explain the basics of naming alkane. We will treat some questions, right? We'll treat some questions, but I will actually release another video where we treat questions on nomenclature only, right? So stay tuned. If you've not subscribed, subscribe. But what I'm trying to say is that okay, let's move on. That will come later. Okay, so there are basically two ways of naming compound, right? There are basically two ways of naming compound. The first one is the systematic way. All right, systematic way. Or name anyhow you want to check it. Names. while the second one is the common names. So we can actually give two names to a particular compound, to a particular organic compound. I'd like to start from the common name, right? So you'll be able to understand what I mean by that. All right, this is actually based on the name given to organic compound based on this methodology, that is common name, is actually meant to reflect the origin, right, history or property of the compound. You understand? So whenever we use this method, it's not actually based on logic. It's not actually based on a particular rule that you say, okay, you have to place this first, you have to place this, you have to do this, you have to do this. It's actually like a trivia name given. I will give you some example. Okay, an ant, the Latin name for an ant is actually known as formica. Okay, sorry, let me change the pen. Okay, formica. The Latin name for ant is known as what? Formica. Okay, now whenever an ant stings you, it actually hurts, right? A sensational pain. You actually feel a sensational pain. Have you ever wondered why such a thing happens? Okay, it's actually due to an acid they contain, which is known as metanoic acid. Metanoic acid. But it's actually the trivial name or the common name is given as formic acid. Formic acid. Formic acid, right? Formic acid. Formic acid. So that's it. It's given as formic acid. So this formic acid I mentioned is the what? The common name. The common name. That is, you cannot really relate, okay, how did they arrive at this name? Okay, if I am in another place, if I'm not Latin, how can I name organic compound there? Right? So it brings about difficulty. The trivial name brings about difficulty. Another example is the vanillin. Vanillin, right? Which is an organic compound derived from vanilla, right? Derived from vanilla. Another one is the acetic acid, right? Derived from where? Vinegar. So over the time, scientists were like, it's actually very, very difficult remembering these names and all. So they came a body, right? They came a body known as IUPAC. You might have heard that. IUPAC, right? So they came about and established a rule whereby all scientists will be guided by, right? Will be guided by and arrive at the correct answer, or arrive at a very generalized naming. Do you understand that? And formic and metanoic acid is one of the systemic names we have. It's one of the systemic names we have. Okay, all these I'm saying are just like stories and history, not that important. Now this video focuses more on the systemic name, right? So let's talk more on the rules to follow and all that. Okay, now the names. So an organic compound, most especially an alkane, can be branched or straight. Now I'll talk about the straight chain. So whenever we see a compound straight, right, how can we name such a compound? So a straight compound or a straight chain alkane. How can we name such a compound when we encounter it? It's very simple. Now, before I explain details, I will give you some examples, some names under alkane that you should know. Right? Let's start. So for the first one, we have methane. Methane. For the second one, ethane. The third, propane. The fourth, butane. The fifth, pentane. Sixth, hexane. Seventh, heptane. Eighth, octane. 9, nonane, and the last one is decane. Okay, so how can we go about this? How can we tell if a particular organic compound of homologous series or functional group alkene, how can we tell if it's methane? How can we also tell if it's ethane? Now, focus on this part, on this very part. They all have what it stands for. They all have a particular meaning they represent. So, whenever I see met, it actually means what? 1. It actually means 1. Right? If you see et, it means 2 carbon. So 1 carbon, 2 carbon. So for propane, 3 carbon. For butane, 4 carbon, the same thing. For pentane, 5 carbon, 6 carbon, 7 carbon, 8 carbon, 9 carbon, and last one, 10 carbon. So these are the guiding rules, right? And if we are, for instance, now they might ask a question, okay, what's the formula of butane? You don't need to even stress yourself. Recall the general formula I said at the beginning of this video. CnH2n plus 2. Just put in your values here. For this one, it's what? 1, so C, 1 times 2, 2 plus 2, 4, H4. All of this, C2, H6, isn't it? C3, H, 3 times 2, 6 plus 2, 8, right? On and on and on and on. If it's octane, C8, 8 times 2, 16 plus 2, 18, H18. So these are the what? The formula of each of them. So for the ones I skipped, you can actually do that on your own. This kind of naming is only when it's a straight chain. So I can actually put a particular example. I can just say, okay, 1, 2, 3, 4, 5, 6, and I'll just ask you, what's the name, right? What's the name of this structure? Don't stress yourself. First of all, find out, is it a straight chain? Yes, it's a straight chain. So name it. Count the number of carbon in a majestic way. 1, 2, 3, 4, 5, 6. As simple as that. So what's 6? Just come here. Don't stress your life. Hexane. Do you get that? The same thing. If it was 8, it was octane. If it was 9, it was nonane. If it was 10, it was decane. It's as simple as that. It's as simple as that. But most examinations might not ask you straight chain. They would like to go further to test how well you understand the topic. Now, that brings us to the next part, which is the branch chain, right? How can we name a branch chain? It's also simple. It's also very, very simple. Okay, this is a question. I'll leave that. I'll explain the branch chain before we solve this question. Sorry? Okay, I'll give an example. It's better explained using an example. So let's assume something like this. Yeah. Let me just put one jar. Okay, so we have something like this, something like this, right? Also like this. Good. Right. So this is not restriction because some of you would like to count 1, 2, 3, 4. Okay, but then you will fail it. You will fail it. You have to what? Be strategic. Now brings us to the second rule, right? So you have to look for the longest chain. You have to identify the longest chain, and that will serve as the parent hydrocarbon. Do you get? You have to find the longest chain. You have to, that's the first step. Whenever you see branching, identify the longest chain. Forget about the substituents. Leave that. First of all, let me just write it so you can note it down. Identify the longest chain. Nice. Identify the longest chain. That's the first step. Now let's identify it. 1, 2, 3, 4. Is this the longest chain? Mba. It's not. Right? Okay, let's go to another route. 1, 2 can never be. Okay, let's try another one. 1, 2, 3, 4, 5. It looks it can be the longest. It can be the longest. So 1, 2, 3, 4, 5. Let's check another one. 1, 2, 3, 4, 5. Nice. 1, 2, 3, 4, 5. Nice. 1, 2, 3, 4. No. Okay. So let's use this. Let's use this. But if you notice, from here down here is also 1 to 5. Right? It's also 1 to 5. From here up here is also 1 to 5. So which one will we go for? That brings us to the second rule. You must assign the least number to the substituent. You must assign the least number to substituent. What does substituent mean? Substituent means all those attachments to the parent hydrocarbon. It's simple. All those attachments are the what? Substituent. Now let's identify the substituent. For here, this can be the substituent. For here, it can be what? Substituent. Let's know if we actually assign the least number to them. So we'll start from here. 1, 2. So here is 2. Nice. 1, 2, 3. 3. This is nice. Okay. Let's try naming it from up. Let's see if it works. Alright, so 1, 2, 3. This 3. 4. No. This it can't work. This 3. This 4. So it's not the least number. Do you get? So we have to make use of these two. That is 2 and 3. Do you get that? We have to make use of 2 and 3. Okay. So how can we name this compound? 1, 2. What was this group called? Let's write it out so you'll be clear. I need you to understand this in details. So this is CH3. What does it tell you? What does this signify? An alkyl group, specifically methyl. An alkyl group, specifically what? Methyl. What is this? The same thing. Methyl. Methyl. In case you are not following very well, let me just recap. The general formula for methyl is CnH2n plus 1. Plus 1. Let's move on. So this is 1, 2, right? So I'll write here 2. Good. 2. Let me write methyl. I'll explain to you how I'll get it. 2 methyl, comma. So we have 1, 2, 3. 3 methyl. Nice. So what's the parent chain? 1, 2, 3, 4, 5. Right? So that looks like pentane. In short, that's pentane. Right? That's pentane. So look at this. I'm repeating myself. Methyl. No, now that's kind of tautology. Right? Let's make it easier. I'll just pick one after the two. So 2, comma, 3, a hyphen, methyl pentane. Do you get the logic now? That is exactly how to name a compound. It's as simple as that. Now let me use another example. Let's try another example so that you're able to get it. Let me clear here. Sorry. Let me clear here. All right. Good. Okay. So look at this. Look at this. Look at this now. CH3 C. Let me write CH. CH3. Okay, let's put here CH32. Let's put here CH32. Let's put here CH3. Okay, please do me a favor. Pause this video. Yeah, pause this video and try to get the structure. Try to get the name, the IPAC name of this compound, of this structure. Yeah, let's try it. So first of all, identify the longest chain. 1, 2, 3, 4. That's nice. 1, 2, 3. Nah. 1, 2, 3, 4. Still the same thing. 1, 2, 3. No. So the longest chain is from here to here. It's as simple as that. Okay. So what do we do next? Assign the least number, right? So assign the least number. Okay. So we can start from here. 1, 2. That is, we're giving 2 to this part and giving 3 here. No. Let's not do that, because it now be 3, 3. We can now start here. 1, 2. So giving 2 here and giving 2 here, then giving 3 here. So it's better. So it's better we start from this angle. That is 1, 2, 3, 4, because it will mean giving the least number to the substituent. Now let's name it. Let's name it. I'm not going to follow this long method, so I'll just go straight to the point. So this is methyl, this is methyl on the same carbon, the second carbon to be precise. I'll write 2, 2. Are you following? 2, 2 methyl. Am I going to write methyl? No, I'm not supposed to write methyl. This is another methyl group. So 2, 2, 3. Right? This 2, and this 3. Sorry, I forgot to mention di. You are going to write di. You get di, since we are talking about 2 methyl here. So 2, 2, 3. Try methyl butane. Try methyl butane. It's as simple as this. Now let me come over again. Let me go over it again so you get to understand. So for this one, because we are 2 methyl group, right? Because we are 2 methyl group here, I have to write di. I skipped it. So please correct it in case you're writing. So I have to write what di to signify there are 2 methyl group. If it was 1, there is no need of me writing anything. If it was 2, then I have to signify. 3, I have to signify. 4, which will be what? Tetra. So for this now, these are 3 methyl group. 3 methyl group. Right? 3 methyl group. And how to signify that? Right? By saying what? Tri-methyl. Do you get? Okay, so that's that for that. And sometimes also, let me clear here. Sorry, let me clear here. It's getting too much. So sometimes you might actually be given a particular compound that you can't only find one substituent, that is maybe only methyl, or probably only ethyl, or probably only just one compound. Sometimes you might have methyl, you might have ethyl, you might have several substituents. So in that kind of case, what should we do? Because all this lecturer or your examiner, we would like to test you on that part. Let me give you a simple question. So let's treat something like let's say 3, 4, 5, 6, 7. Okay, so know that this will be 1, 2, 3, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 3. Good. So let me just put okay, 1 2 3. Okay, let me just put CH3 here, and for here let me just put C2H5. Okay, that's nice. So in this kind of case, how can we name it? It's obvious that this is the longest chain. It's so obvious. It's so obvious, right? So let's know what the parent hydrocarbon will be. 1 2 3 4 5 6 7. So it will definitely end with what? Heptane. Okay, that's not all, right? So let's assign the least number to the substituent. Should we start from here? 1 2 3 4. 4 5. No. Let's start from this side. 1 2 3 4. This look nice. So I'll now say, now here's the problem. You know, we now have 3 methyl. We also have 4 ethyl. Which one should come first? Which am I to write first? Should I write 3 methyl or 4 ethyl? Okay, whenever I see something like this, you have to name it in order of increasing size or alphabetical order. In order of increasing size or alphabetical order. Okay, so in this one, A, B, C, D, E. E comes before M alphabetically. So I'm going to write 4 ethyl, right? Please remember your hyphen here. 4 ethyl. Good. Another hyphen. 3 methyl heptane. As simple as that. If you don't understand it, please comment in the comment section. I'll be able to give a reply to that. So now let's treat the first question. There's really so the following are members of the alkane, except which of them? Pause this video and try it ASAP. Now let's continue. This is second carbon, CnH2n+2. This is the formula we'll be using. Nothing that's stressing your life. So 2, put 2 here. 2 times 2, 4, plus 2 is what? Plus 2 is what? 6. So this is correct. All this 8, put 8 here. 8 times 2 will be what? 16. 16 plus 6 is what? 18. So this is also correct. Let's put 12. 12 here. 12 times 2, 24. 24 plus 2, 26. Let's check this. We might be wrong. You know, let's check this. So 15 here. 15 times 2, 30 plus 2, 32. So this is actually correct. This is the scapegoat. This is the wrong option, right? This is the wrong option. So now let's move to the second question. All right. So question 2, they asked the carbon atom of propane are dash. The carbon atom of propane. Forget this big grammar. This propane identity. Forget it. Let's look at the functional group N. Remember, I told you for ANE, right, is what? sp3. Abi, are you forgotten? So EN is what? sp2. Of YNE is what? sp. So now let us pick it. Not hybridize. sp2 hybridize. No, that's for alkene now. That's for alkene. Have you forgotten? That's for alkene. Okay, so what of D? No, that's for alkyne. So this is wrong too. So it has to be this. This is correct. As simple as that. It's very simple. Now let's move to the second one. Okay, so they asked the orbital that overlap in methane. The orbital that overlap in methane. Now let's look at this. This is methane, right? When they mean overlap, they mean something that comes together, like coming together to probably form a bond or whatsoever, to probably form a bond in most cases. Okay, so this hydrogen, it has only one valence electron, and that one valence electron is actually in the s subshell, right? It's actually in the s subshell. And remember, this has been hybridized to be given sp3. You get? So how is it going to overlap now? Since there are only hydrogen here, the overlap will be between sp3 and s, going for this. C is very correct. Do you get? C is correct. sp2 is out of it because we are not talking about alkene here. sp is also out of it because we are not talking about alkyne. S and S are bound now. It can't be that. Now let's go to the next one. Alright, look at this structure. All of you running for structure, you will choose structure. Don't worry. From now on, we'll just be choosing structure. Okay, let's name this. Let's name this very simple. Okay, pause this video again and try naming it. Now let's look for the longest chain. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4. No. 1, 2, 3, 4, 5. Sorry, not 6, 5. So without even without even knowing the correct answer, I know that my answer will be between this and this. Okay, let's continue. So this is 1, 2, 3, 4, 5. So 1, 2, 3, 4. So we can either give this 4 or we can give this what? 2. We'll start from here. We'll start from this part, since this will give the least number to the substituent. So it will be what? 2-methyl pentane. This is correct. Option D is correct. Option D is correct. Now go to the next question. Now let's name this. We have something very funny here. We have bromine. Alright, anyway, it's also simple. Don't need to panic. The longest chain, 1, 2, 3, 4. Nice. Right? The longest chain, 1, 2, 3, 4. So we can either pick it like this or like this. Right? So I would like to pick the horizontal one, which is like this. You get? So let's pick it. 1, 2, 3, 4. I can give this 2 and give this 2. Or if I'm going this way, I can give this 1, 2, 3, 4. Right? That is 3. Giving this 3 and 3. Which one do you think we should follow? Should we follow like this or this way? Definitely to the right. Right? I should follow this part. Do you get? Okay, so to name it, I already know that my answer will end what? In butane. I know already that my answer will end in butane. So let's name it 1, 2. So 2 bromo. We have 2 bromo. We also have 2 methyl, then butane. Do you get? Okay, so not only that, which one should come first? Because arrangement also matters. Arrangement also matters. Now B comes before M. Definitely we'll say what? 2 bromo, 2 methyl butane. So C is correct. C is correct. Go to the next one. The IUPAC name of this compound. Oh, sorry, I didn't draw the compound. Okay, but this is how the compound is. This is how the compound is. So I have something like this, right? Or something like this. Then it's substituent. It's substituent. It's substituent. It's substituent. Okay? It's substituent. Something like this. So how can we name it? It's so simple. The longest chain, which is this part, right? That longest chain. So it will be 1, 2, 3. We can give this 3, or we can give this 1, 2, 3, 4. From this direction, it will be 4. So we have to follow this part since it gives the lowest number to the substituent. So it's what? 3-methyl-hexane. 1, 2, 3, 4, 5, 6. 6 signifies the number of carbon, which is what? Hexane. Option B is correct. Alright, so the IUPAC name for this compound is, pause this video and attempt it. Welcome back. Look at this. It's very, very tricky, but it's also simple. Yes, now. So look at this. We can pick 1, 2, 3, 4. But if I'm picking 1, 2, 3, 4, how can we name this stuff? How can we name this guy? Like, how can we name this guy? Okay, so see, this is here. You have to give more priority to this particular chain, to this particular flow. And you have to give more priority to it. So instead of me starting from this end by saying 1, 2, 3, 4, no, I would like to start from this. You get? I'll start from this end. So it will be 1, 2, 3, 4, like something like this. You get? So now it was one chloro. We have one chloro, right? Also we have two. We have two. This will be 3, not 2. So we have 2 methyl 2. Right, then we have 1, 2, 3, 4 butane. I'm sure you have seen your answer already. Okay, that's fine. So we can just say 1, 2, 3, 4. You get? So which one comes first? Is it chloro or methyl? Chloro comes first because of C comes in alphabetical order. C comes forward. Methyl. You get? So we have 1 chloro 2 methyl butane. It's as simple as that. Option B is correct. Now we have 3 more questions to go. Okay, 2 more now. So just complete. Let me complete it, please. Let me complete it. I'm feeling lazy. Let's continue. Let's name this. So let's name this. So we can either start from here or start from here. We can start from the left or start from the right. But that doesn't matter. It's what matters is that we give the least number to the substituent. Now, if we start from this particular end, we will not get the least number to the substituent. Look at how far it is now. Now, I get it. So we have to start from the left. You get? We have to start from the left. So we will now have something like 2,2-dimethyl. Let's start from there first, because this is 2,2. So 2,2-dimethyl. Is that all? No. This is another one. We have 3, 4. So 2,2,4-trimethyl. Right? Something like this. So moving on. We now have 1, 2, 3, 4, 5. With 1, 2, 3, 4, 5, 6. So which is what? Hexane. Right? What's the answer? Option D. Option D is correct. Option D is correct. Now let's move to the next question. The least but then last. So let's name this. Also simple. It's also simple. Right? So we can either start from the right, the left, or from the right. It doesn't matter, but we must ensure that we give the least number to the substituent. Okay, let's start from here. 1, 2. This is 2. This 2, right? This 3, right? This which other substituent are here? No one. Okay, this okay. Voila to do. Okay, let's move on. It's simple. Now this is 1, 2, 3, 4, 5, 6, 7. You get? The longest chain is what? 7. The longest chain is what again? 7. So let's try and go in this direction and also go in the next direction and check which one which will now pick the one we choose. So this is 1, 2. So we have like 2 methyl. Nice. This now, how can we name this particular stuff? We can't name it methyl. But now we cannot name it except this one is at this particular end. You get? In this kind of case, we will name it as a compound, like as an entity. So whenever a compound or an organic compound has 2, it will be directing toward ethyl. So this is what? 3-ethyl. Nice. 3-ethyl. So 1, 2, 3, 4, 5, 6, 7. 6, 7, 6. So this one is on the 6th carbon. So we have 6 methyl. So we have 6 methyl, right? Now let's go in the next in this direction. Let's see which one we should choose. Okay, 1, 2. So you can either say 2 methyl 2, right? 2 methyl. 1, 2, 3, 4, 5. So 5-ethyl, right? 6 methyl. Hey boo. Okay, short. Which one should we go for? Oh yeah, pick. Which one should we go for? The first one. We should go for the first one, right? We should go for the first one. right? Because look at this now, 5 now, look at this now, 3. How about? So we have to go for the first one. So now we've identified the substituents, we've identified the parent chain, and we know that the parent chain has to be heptane. 1, 2, 3, 4, 5, 6, 7. So heptane now, she gets. Okay? Not only that. Now let's arrange it. This will come first. E comes before M. So we have 3 methyl, 3 ethyl, 2 6 di because there are 2 methyl group here. So 2 6 dimethyl what? Heptane. As simple as that. Do you get? Option A is correct. Option A is correct. Now to the final question. Okay, this is very straightforward. In short, I'm not going to stress myself. Pause this video, try it, ensure you get it. If you don't get it, I'll come to that place. So ensure you get it. Okay, let's move on. So we have 1, 2, 3, 4, 5, 6. Do you get? So we know that the parent chain has to be what? Hexane. Okay, so 1, 2, 3. So we are assigning 3 here. This is 4. Okay, let's start from the other end. This is 4. Let's start from the other end. 1, 2, 3, 3, and here 4. wow. So which one should we give? Look at this. This is 3. If I start from this side, and this is what? 4. This 3. If I start from what? This side. Now, which one should we follow? Should we start from the left or from the right? I need you to think critically now. Remember, I told you that another thing that contributes to naming is in alphabetical order. We must name in alphabetical order. You understand? So because of that, B comes before methyl now. Normal. B comes before what? Methyl. Therefore, we give more preference to this bromine here, the bromo compound here. Do you understand that? So instead of me saying 3 methyl, I say what? 3 bromo. So 3 bromo. That's the first one. And 4 methyl. Right? This is what? The parent hydrocarbon. So now just go to your option and pick the correct one. 3 bromo, 4 methyl hexane. As simple as that. Can you see? C-trap. Is in option A. Option A. So B is the correct answer. Do you get? B is the correct answer. Alright. Thank you so much for watching this video. Thank you so much. I really appreciate it. And I promise that we will continually upload new videos. But you know, we cannot upload videos. Yeah, we will upload videos always. But there are some of you out there, in short, some of you who are watching me right now, right, who would like to know more about a particular concept, who would like to partner with us, right, to learn more. Or some of you might be preparing for exam of any kind, JAM, UTME, POSITME, JUPEP. We offer that at Gallant Tutors at a very affordable price. You'll be guided by expert tutors. Now, without wasting much of your time, let me explain to you some of the programs offered here very quickly. Right? So for this program is mainly for post-UTM students. Right? So if you're a post-UTM student, you're welcome. So we unveil some of the programs we'll be offering. The first one being I'll start from here, Edu Nexus Hub, right? The second, Elite Circle or Elite Scholar Circle. This, the Operation Ultimate Precision. This, the Final Rectification, the retrospection class, I mean to say, right? All these programs are important, but you must not be in everything. Yeah, you must not be in everything. So just follow me as I explain to you each and every one of them. Okay, most of you have problem identifying, okay, sir, which one should I go for? Should I go for Elite Circle, or should I go for Operation Ultimate Precision, or will I just go for Edu Nexus Hub, jelly? Just follow me, just focus on me. Nice. Okay, I'll start from this first one. Operation Ultimate Precision. This is meant for those of you who need special care. You understand? who need special care, who needs a detailed guidance, one who will follow you up bomber to bomber, this program is meant for you. Also, most of you that find it hard to read personally, to dedicate 7 hours daily to reading, this is also for you. Or are you a person that works or cater for yourself, but you just need a tutorial that will not hinder you at still continuing your job? This is also for you. We have the best services, the best feature you can ever think of an online tutorial. And it's very affordable, with the sum of 5,000 naira. You join us. Yes, with the sum of 5,000 naira only, you gain access to this. Now let's go to the next one, the Elite Scholars Circle. There are some of you, some like me, that doesn't like attending class. We just like prefer studying on our own, right? We prefer exploring on our own. To get something like that. You might be someone like that. This Elite Scholar Circle is for you. You won't be taught by any teacher, never, right? But the only privilege you have is that you have access to our experts, to our tutors. So sometimes when you don't understand the concept, or when you don't know how to solve a particular question, you can just send them a message. Oh, hello sir, please, I would like you to explain this question to me. They will explain to you in details. Yes, that's the access I'm talking about. So that's not the main feature. The main feature is that this is just like a pair learning program whereby you meet others, right, who are in the same category as you, right? You interact, you brainstorm. And unlike the normal brainstorming session we do know that are being organized on WhatsApp, this is special in that you are being guided by mentors that will tell you, okay, this is not the right thing to do, this is not the right thing to do, do it this way and that. So Elite Scholar Circle is also very affordable at the rate of what? 3,000 naira only. 3,000 naira only, or $5. Alright, Nexus Hub. There are some of you that, in short, you lack access to real-time information, right? You don't even know much about the school you applied for. You just know that, I'll write PUSITM one day, I'll write PUSITM, I'll buy form. That's very wrong. Ignorance is costly. You get, like, is detrimental to see. It's very detrimental. So this Nexus Hub guide you. Okay? For instance, you are trying to study medicine in Unilag, but you had 270. That kind of stuff can get you a course. It can never get you medicine in Unilag, that's for sure, right? But it can give you a better course in which you'll be given the privilege to switch back to medicine when you perform better in 100 level. This Nexus Hub will take you through that process, and guess what? It's just a one-time payment. That is, when you pay once, it's a lifetime. Not only that is not only about the consulting service that Nexus occur. We help to develop your mindset to acquire a very superior one. Therefore, you will be distinguished from your peers. In short, when you interact with them, they'll be like, what happened? You changed completely. That's the power of Nexus Hub. Alright, that's it. And the price? Just 2,000 naira. You gain access to it. Here are the price and the summary of the features. Alright, thank you so much for following me through my explanation and everything. I really appreciate it. Thank you so much. God bless you. Bye.